There's a lamp on the table tonight. Its light is steady and warm, falling in a small circle across the wood, and beside it, resting where you might set a book you've been meaning to open, there's a book. The spine is uncracked. The cover is unmarked. It's simply there, waiting. Tonight, you and I are starting something new. We're going to spend this season together looking at a question that seems straightforward at first. The kind of question you might ask a child over breakfast. What is the universe made of? It turns out the answer is mostly written in ink we can't yet read. Not because the universe is hiding, not because we're not looking carefully enough, but because most of what holds everything together, most of what fills the space between stars and galaxies and the chair you're sitting in, most of it doesn't interact with light the way ordinary things do. We can't see it directly. We can't photograph it. We can't touch it or taste it or weigh it on a scale. But we know it's there because we can see what it does. And that knowing, that patient, careful noticing, is what this season is about. The book is on the table. The lamp is on. We've got time. Let's open the cover. If you wanted to bake a cake, you'd need a recipe. Flour, sugar, eggs. You'd need to know how much of each and in what proportions. Too much flour and the cake is dry. Too little sugar and it doesn't rise. The recipe tells you what goes into the bowl and in what balance. The universe, it turns out, has a recipe too. And after decades of careful measuring, after building telescopes that can see in wavelengths our eyes can't detect, after listening to the faintest whispers of light that have been traveling for billions of years, we've finally been able to read it. The recipe comes from what scientists sometimes call a baby picture. It's the oldest light in the universe, a faint glow that fills all of space. It was released about 380,000 years after the beginning, long after the initial moment, but still unimaginably early in cosmic terms. Back then, the universe was small enough and hot enough that it glowed, like the inside of a warm oven. That glow has been cooling and stretching ever since. Today we call it the cosmic microwave background, and hidden in the tiny temperature variations across that glow, variations so small you'd need instruments to detect them, is the recipe, the proportions, the inventory of everything that exists. Here's what it says. About 5 parts in 100 are what we'd call ordinary matter. Atoms, protons and neutrons, the stuff stars are made of, the stuff you and I are made of. About 27 parts are something else, something that doesn't glow, doesn't emit light, doesn't interact with photons at all. We call it dark matter. We know it's there because of the way galaxies move, the way light bends around massive objects, the way structure formed in the early universe. It acts as scaffolding. It holds things together. And the rest, almost 68 parts in 100, is something even stranger. It's not matter at all. It's a kind of gentle, persistent pressure that seems to live in space itself. It's making the universe expand faster and faster, very slowly, over billions of years. We call it dark energy. Back here by the lamp, those numbers might feel abstract. So let's put it this way. Imagine the book on the table has 100 pages. You open it, and you find that you can read about 5 of them. The words are clear. The sentences make sense. You recognize the grammar, the structure, the meaning. But the other 95 pages, they appear blank, not torn out, not missing. The pages are there. You can feel the weight of them. You can see the binding holding them together. The chapters seem to flow from one to the next, as if something connects them. But when you shine the lamp directly on those pages, there's nothing you can see. No ink that reflects the light back to your eyes. And yet the book holds. The spine is solid. The pages turn. Something is written there. You just don't have the right kind of light yet. That's where we are. 5 pages we can read. 95 we can't. Not yet. But we're not alarmed by that. We're not anxious. If anything, we're curious. Because here's the thing. This isn't a book that's going to test you in the morning. It's not a puzzle you need to solve before you can rest. It's simply here, on the table. An invitation to wonder. And wondering, it turns out, is one of the kindest things the universe offers. We don't need to read the whole book tonight. We've just opened the cover. Let it rest on the table for a moment. The lamp is still on. The room is still quiet. And we've got all the time we need. In our solar system, the planets farther from the sun orbit more slowly than the planets closer in. Mercury, hugging tight to the sun's warmth, completes its orbit in just 88 Earth days. It races around the sun, fast and close, pulled hard by gravity. Neptune, out in the cold dark, takes 165 Earth years to make the same journey. It crawls through its orbit, distant and slow, barely tugged by the sun's distant pull. Between them, the other planets follow the same pattern. Venus faster than Earth, Earth faster than Mars, Mars faster than Jupiter, each one a little slower than the one before as the distance grows. This isn't arbitrary or random. It follows directly from gravity, from the mathematics Isaac Newton wrote down centuries ago. The sun's gravity pulls hardest on Mercury, gently on Neptune. Less gravitational pull means a slower orbit, a gentler curve through space. If you could somehow move Neptune closer to the sun without changing anything else, it would speed up, forced into a tighter, faster path. If you pushed Mercury outward, away from the sun's pull, it would slow down, settling into a longer, more leisurely orbit. This pattern, fast near the center, slow at the edges, is what we'd expect anywhere gravity works the same way. It's a universal principle, as reliable as the sunrise. So when astronomers turned their telescopes to galaxies, vast collections of billions of stars, bound together by gravity, they expected to see the same pattern there. Most of a galaxy's visible light comes from its bright center, where stars are packed densely together, crowding close like people in a city center. The edges are dim, sparse, scattered. The light thins out as you move away from the core. Light marks where the mass is. That's been true throughout astronomy. Bright means massive, dim means sparse. And if most of the mass is concentrated in the center, then stars at the outer edges should be orbiting slowly, gently, like Neptune crawling through its long year. Think of it like a book on the table in front of us. The pages are heavier near the spine, where the binding holds them tight, where the paper is layered thick. The margins are lighter, thinner, easier to lift. The weight is concentrated where the structure is. If you were to spin the book, the spine would pull harder than the edges. That's what we expected to find in galaxies. That's what the mathematics predicted, what decades of work with Newton's equations told us to look for. Fast rotation near the bright center, where the mass is. Slow rotation at the dim edges, where the mass thins out and the gravitational pull weakens. But when scientists finally developed the tools to measure the speeds carefully, out at those dim edges where the light fades into darkness, that's not what they found. In the late 1960s and through the 1970s, two astronomers, Vera Rubin and W. Kent Ford Jr., began measuring how fast stars were moving at the outer edges of spiral galaxies. This was technically difficult. The edges of galaxies are dim, very dim. The stars out there are sparse and their light faint, barely reaching us across the vast distances of space. Previous instruments couldn't gather enough light to measure their speeds reliably. The signal was too weak, the data too noisy. But Kent Ford had built something new, an image tube spectrograph that could amplify faint light, turning whispers into measurable signals. It made it possible to measure the speeds of stars in regions no one had been able to study before. The far edges, the dim outskirts, the places where galaxies fade into the dark. It was patient, careful engineering. Not dramatic, not flashy, just effective. The kind of work that takes years to perfect, that solves one technical problem after another, until finally, quietly, it works. In 1970, Rubin and Ford published a study of the Andromeda Galaxy, M31, the nearest large spiral galaxy to our own. They measured the speeds of stars far from the center, out where the visible light fades into darkness, where you'd expect everything to be moving slowly. The outer stars weren't slowing down. They were moving at about the same speed as stars near the center, roughly 200 to 250 kilometers per second. Fast. As fast as the inner stars, as fast as stars surrounded by all that concentrated light and mass. The rotation curve, as it's called, was flat, not declining, not tapering off the way Newton's gravity said it should. Just flat, level, as if something unseen were holding those distant stars in a faster orbit than the visible mass could account for. It was unexpected, puzzling, but one galaxy might be an anomaly, a quirk, an exception to the rule. So they kept measuring, galaxy after galaxy, patiently, methodically. In 1980, Rubin and Ford published a comprehensive study of 21 spiral galaxies. They found the same pattern in every single one. Flat rotation curves, outer stars moving as fast as inner stars, even though most of the visible light, most of what we assumed to be the mass, was concentrated in the center. The data was too consistent to dismiss, too clear across too many galaxies. Vera Rubin turned what had been a fringe curiosity, a strange observation noted by a few, into undeniable evidence. The numbers didn't match the expectations. Something was missing from the picture. It was as if every book on the shelf weighed the same at the margin as it did near the spine. As if something unseen were adding weight to the edges, holding them steady, keeping them from sagging under their own lightness. The lamp still glows on the table. The book is still here, the pages turning under our attention. And we've just read the first clue. Galaxies don't spin the way they should, if only visible matter is present. The flat rotation curves mean something specific. There is much more mass in a galaxy than the stars and gas we can see. Roughly 5 to 10 times more. But that invisible mass isn't distributed the way the visible matter is. The stars and glowing gas we photograph are concentrated in a flat disk at the center. The beautiful spiral arms you see in pictures, bright and photogenic, the iconic image we think of when we picture a galaxy. That bright disk might stretch 50,000 or 100,000 light years across, a vast pinwheel of light spinning in the darkness. But the invisible mass forms something different. A vast, roughly spherical halo that surrounds the visible galaxy and extends far beyond it. It reaches perhaps 100,000 to 300,000 light years from the center, 2 or 3 times the diameter of the visible disk. The bright spiral, the part we photograph and study and marvel at, is just a small circle sitting inside this enormous, invisible sphere. Picture the lamp on the table again. The light makes a bright circle on the surface. Clear, well-defined, easy to see. The edges are sharp. You can point to where the light stops. But the room extends well beyond what the lamp illuminates. The walls are out there in the darkness, a few feet away, maybe 10 feet, maybe more. The corners are dim. The far edge of the room is invisible from here. But the room doesn't end where the light does. The frame of the house doesn't stop at the edge of the lamplight. It continues, hidden, holding the structure even in the darkness. The visible galaxy is the lamplight. The dark matter halo is the room. This was the first clue, the first page turned. Galaxies spin in a way that only makes sense if most of their mass is invisible, spread in a vast sphere around the bright center we've been photographing for more than a century. The rotation curves told us this. The numbers demanded it. And once scientists knew to look for this hidden mass, once they understood what the rotation curves were telling them, they found it again, in a completely different way, using completely different physics, looking at a completely different phenomenon. Let's turn that page now. There are bookshelves in this house, sturdy ones, the kind that hold a lot of weight. Rows of books stacked too deep in places, heavy volumes with thick spines. You've probably got shelves like that in your own home. You trust them. You don't think about them much. But if you look closely, if you really pay attention, you might start to wonder, what's holding them up? The brackets, sure. But where are the brackets anchored? What's behind the wall? Is there a frame? Studs? Something solid that the screws bite into? Something that keeps the whole structure from pulling free? You can't see that frame. It's behind the plaster, behind the paint. But you know it's there, because the shelves don't fall. That's dark matter. It's the structure you can't see. The frame behind the wall, the scaffolding that holds everything in place. And without it, without that invisible support, nothing would stay on the shelf. The books would tumble, the walls would sag, the house as we know it wouldn't stand. In the late 1960s and early 1970s, an astronomer named Vera Rubin started measuring something that seemed straightforward at first. How fast stars move inside galaxies. She worked with a colleague named Kent Ford. Together, they pointed their instruments at spiral galaxies. Galaxies shaped like pinwheels, with arms sweeping out from a bright central bulge. and they measured the speed of stars at different distances from the center. They expected to find what Newton's laws would predict. Stars close to the center, where most of the visible mass is concentrated, should move fast. Stars farther out, where there's less visible mass pulling on them, should move slower. That's how planets work in our solar system. Mercury, close to the Sun, orbits quickly. Neptune, far from the Sun, crawls along in comparison. But that's not what Rubin and Ford found. The stars at the outer edges of galaxies were moving just as fast as the stars near the center, sometimes even faster, as if something invisible, something they couldn't see, was holding the galaxy together, adding mass, adding gravity, keeping those outer stars from flying off into the dark. It was a bit like watching a carousel where the horses at the very edge spin just as fast as the horses near the center. Something unseen must be pulling them along. Back in the room, we can think of it like this. The walls of the house are standing firm, held by a frame we've never seen directly. The visible paint, the plaster, the shelves themselves, those are the stars. But the studs, the beams, the skeleton of the structure, that's hidden. And yet, without it, nothing stands. In 2006, astronomers observed something extraordinary. Two massive clusters of galaxies, each containing hundreds of galaxies, vast clouds of hot gas, and all the dark matter bound to them, had collided. When galaxy clusters collide, the galaxies themselves mostly pass through each other. Space is big, stars are small. Collisions between individual stars are rare. But the hot gas, the gas that glows in X-rays, the gas we can photograph, that gas slows down. It crashes into itself. It clumps. It gets left behind, like two clouds of steam meeting and tangling together. And yet, when scientists measured where most of the mass actually was, not by looking at the gas, but by measuring how the cluster bent light from even more distant galaxies behind it, using a technique called gravitational lensing, they found that the majority of the mass had kept moving. It had passed right through. The gas was in one place. The gravitational mass, the thing doing most of the pulling, was somewhere else entirely. It was separated. It's a bit like noticing the shelves have shifted, but nothing visible pushed them. The books are still there. The wood is still solid. But the frame, the thing actually holding everything up, moved on its own. This is as close as we've come to seeing dark matter's influence with our own instruments. We can't photograph the dark matter itself, but we can photograph where it isn't, and where the ordinary matter got left behind. And that separation tells us, dark matter is real. It's not just a mathematical trick. It's not just a gap in our theories. It's there. So what is it? Scientists have names for what it might be. Candidates, possibilities. One leading idea is something called WIMPs, weakly interacting massive particles. These would be particles that have mass, that respond to gravity, but that almost never interact with ordinary matter. They'd pass through you, through the earth, through the walls of this room, like ghosts passing through a house they no longer live in. Another candidate is something called an axion, a much lighter particle, predicted by certain theories, that could fill space in vast numbers. Detectors with names like Lux Zeppelin and ADMX are listening, watching, waiting for a signal. So far, There's been silence. Not because the detectors aren't sensitive. They are. Extraordinarily so. But dark matter, if it's made of these particles, is extraordinarily shy. It doesn't want to be caught in the act. And that's all right. Science is patient. The search continues. We haven't identified the carpenter yet. We've just noticed the carpentry, the joints, the fit, the way the house holds together even when we can't see the nails. And that's enough for one chapter. We can leave a bookmark here. The shelves are still standing. The lamp is still on. There's nothing urgent to resolve tonight. The frame is there. We know it by what it does. And for now, that's enough. Now let's shift our attention to something even quieter. Not the furniture, not the shelves, not the books or the lamp or the walls themselves. The space between them. The room itself. If you could measure the distance between the chair you're sitting in and the window across the room, if you could measure it with the kind of precision astronomers use, measuring distances across billions of light years, you'd find something strange. That distance is getting larger. Not quickly, not violently, not in any way you'd ever notice in a human lifetime, or 100 human lifetimes, but slowly, patiently, over billions of years, the space is growing. It's as if the house itself is quietly, imperceptibly adding rooms. Not by building new walls, but by stretching the space between the walls that already exist. The distance between the chair and the window, if you could measure it in cosmic terms, is getting just a little larger. And that stretching, that gentle expansion, is what we're going to talk about now. In 1998, two teams of astronomers were trying to answer a simple question. Is the universe's expansion slowing down? It seemed like a reasonable thing to expect. After all, if you toss a ball into the air, gravity pulls it back. The ball rises quickly at first, then slows, then stops, then falls. The expansion of the universe, born in the initial moment we sometimes call the Big Bang, should work the same way. The mutual gravity of everything pulling on everything else should slow the expansion over time. So the two teams, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, set out to measure that slowing. They looked at distant exploding stars called Type 1a supernovae, which are extraordinarily useful because they all explode with roughly the same brightness. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate how far away it is. And the farther away a supernova is, the longer its light has been traveling, which means you're seeing it as it was in the distant past. The teams measured dozens of these supernovae, some billions of light years away, some closer, and they plotted the data. And the data said something unexpected. The distant supernovae, the ones from billions of years ago, were dimmer than they should have been. Not because they were different, but because they were farther away than expected. Which means the expansion wasn't slowing down. It was speeding up. Imagine tossing a ball into the air and watching it rise faster the higher it climbs. Something is pushing. Sitting here by the lamp, that push doesn't feel urgent. It doesn't feel alarming. It's patient. It unfolds over billions of years, not over the course of an evening. But it's there, and it's real. In 2011, Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics for the discovery. So what is it? What's pushing? Scientists call it dark energy. But that name can be a little misleading because it's not a fluid. It's not a gas. It's not a wind blowing through space, or a substance you could bottle, or a force you could shield yourself from. It's more like a quality of space itself. Everywhere, all at once, quietly persistent. One way to think about it, and this is still a hypothesis, still something scientists are testing, is that empty space has energy. Not because something is in the space, but because the space itself, by virtue of existing, carries a kind of tension, a slight outward pressure. The more space there is, the more of this energy there is. And as the universe expands, as space grows, the push grows too. Very slowly, very gently, but it adds up over billions of years. Albert Einstein once guessed at something like this. In 1917, he added a term to his equations, something he called the cosmological constant, to balance the universe and keep it from collapsing under its own gravity. Later, when Edwin Hubble discovered that the universe was actually expanding, Einstein called it his biggest blunder. But it turns out the universe may have agreed with Einstein's first guess after all, or something very close to it. Here in the room we can think of it like the warmth, not the warmth from the lamp, that's localized, concentrated, but the warmth of the room itself, the air, the walls, the background temperature. You can't point to it. You can't say it's coming from one place. It's simply everywhere. Dark energy is like that. Not something placed in the room, but something the room itself has, by virtue of being a room. Very recently, in 2024, just a few months before tonight, a massive new project called DESI, the Dark Energy Spectroscopic Instrument, released its first-year results. DESI is looking at millions of galaxies, measuring their distances and positions, mapping the structure of the universe in extraordinary detail. And in that data, there's a hint, a whisper. The hint is this: the push might not be constant. It might be changing over time. Not dramatically, not conclusively. The significance is still below what scientists call a discovery threshold. But it's there, a small suggestion in the numbers that dark energy may not be the simple, steady cosmological constant Einstein imagined. It might be something more dynamic, something that evolves. This is one of those places where the chapter is still being written, where the ink is still drying, where we're learning as we go. And that's all right. The push is quiet. It doesn't rush. It's been unfolding for billions of years, and it will continue for billions more. We don't need to solve it tonight. We can set this thought on the shelf and leave it resting. The lamp is here. The room is warm. There's no urgency. Just a gentle, patient expansion. Like the house adding rooms in the dark, one careful breath at a time. Back here by the lamp, there's something worth saying about the word we've been using. Dark. Dark matter. Dark energy. It's the word that appears in every headline, every article, every conversation about the 95% we can't see directly. But the word needs a moment, because in everyday language, dark carries weight. It suggests shadow, mystery, sometimes even danger. The dark corner of a room, the dark woods in a fairy tale, the place where you can't see what's coming. But that's not what dark means here. In physics, in astronomy, dark simply means not interacting with light in ways we can currently detect, not emitting light, not absorbing light, not reflecting it, scattering it, or bending it in ways that would make it visible to our eyes or our cameras. Transparent might be a more accurate word, or simply unread. Think of it this way. You're holding the book, the lamp is on, and when you turn to those 95 pages, you don't see words. Not because the pages are sinister, not because they're hiding from you, but because the ink they're written in doesn't reflect the particular wavelength of light your lamp happens to emit. Maybe the ink is written in infrared, or ultraviolet, or some spectrum we haven't invented a detector for yet. The words may be there. The information may be complete. You just don't have the right kind of light. That's what dark means in this context. It doesn't mean absent. It doesn't mean threatening. It just means not yet legible. And here's something else worth noticing. Dark matter and dark energy are not the same thing. They share the word dark. They both represent parts of the universe we can't see directly, but they appear to be entirely different chapters, not the same story, told in different ways. Two separate unknowns. Dark matter is structural. It holds things together. It's the frame behind the walls, the scaffolding that keeps galaxies from flying apart, the gravitational glue that allowed stars and planets to form in the first place. It pours. Think of it as the frame of the house, the beams, the support, the thing that keeps the roof from collapsing, the walls from buckling. You can't see it when you walk through the rooms, but without it, there would be no rooms to walk through. Dark energy, on the other hand, is expansive. It pushes things apart, very gently, very slowly, but persistently over billions of years. It's not a frame, it's not a structure, it's the growing of the space itself, the way the rooms seem to stretch, the way the distance between the furniture and the walls increases, not because anything is moving through the room, but because the room is quietly adding space to itself. Think of it as the openness, the air, the space between. And as far as we can tell, these two things, the frame and the openness, are unrelated. They don't come from the same source. They don't serve the same function. They just both happen to be invisible to the kind of light we've learned to see with. One holds, one stretches. Two different mysteries, written on two different sets of blank pages. So here we are, sitting in a universe where most of what exists is invisible to us, where the recipe is 95% ingredients we can't taste, can't touch, can't photograph. And one way to respond to that might be with frustration, or anxiety, or the feeling that we're missing something crucial, something we ought to understand before we can rest. But there's another way to think about it. What does it mean that most of reality is invisible to us? It means the universe is more than we thought, larger, stranger, more full of possibility than any story we could have written for ourselves. It means that science, real science, not the tidy version from textbooks, but the living, breathing practice of asking questions and looking carefully, is honest enough to say, we don't know. And that honesty is beautiful. Not knowing isn't a failure. It's not a gap that needs to be filled before you can feel settled. It's simply the condition we live in, the condition we've always lived in. Humans have never known everything. We've never had the whole book in hand. And yet, we've built houses, we've made tea, we've looked up at the stars and told stories, and held each other through the dark. Not knowing is its own kind of quiet. It doesn't demand anything from us tonight. It doesn't ask us to solve anything, or fix anything, or figure out the final answer before morning. It just invites us to wonder, to sit with the question, to let the blank pages rest on the shelf, knowing that someday someone might find the right kind of light. But not tonight. Tonight, we can let it be. The lamp is still on. The book is still open. And the mystery, the quiet, patient mystery of the 95%, is simply here. Like the warmth in the room, it doesn't need to be resolved. It's enough, just as it is. Let's look back for just a moment at what we've held tonight. We opened a book. We looked at the recipe for the universe, the inventory, the proportions, the list of ingredients that make up everything we know. And we found about 5 parts in 100 are ordinary matter. Atoms, stars, dust, oceans, you. About 27 parts are the invisible scaffolding, dark matter, the frame behind the walls, the structure that holds galaxies together and keeps stars from drifting apart into open space. And the rest, almost 68 parts, is the gentle push, dark energy, the quiet, persistent stretching of space itself, making the room a little larger with each passing billion years. We met the evidence, Vera Rubin's spinning galaxies, the bullet cluster's separated mass, the distant supernovae, dimmer than expected, and the baby picture of the cosmos, the cosmic microwave background, showing us the proportions written into the universe's earliest light. And we learned that the word dark doesn't mean dangerous or missing. It just means not yet legible. Pages written in ink our lamps can't read. Not absent, just unread. That's what we've held. That's what we've opened. And it's enough for one night. There's more on the shelf, of course. More chapters, more questions. In the episodes ahead, we'll look more closely at the scaffolding, at what dark matter might be, and where the search is taking us. We'll explore the push, the strange quiet force that's stretching the universe, and the tension in the measurements that suggests we might not have the whole story yet. We'll talk about the cosmic web, the vast structure of filaments and voids that connects galaxies across billions of light years. We'll talk about the measurements that don't quite agree and what that tension might mean. And we'll ask the question that lives at the edge of every cosmologist's mind. Where is all this going? But those are chapters for another night. Tonight, we've simply opened the cover. We've looked at the table of contents. We've seen the shape of the book, felt the weight of it in our hands. There's more on the shelf, whenever you'd like to come back. No rush, no deadline, no test in the morning, just an invitation. The book is back on the shelf now. The lamp is still on, casting its small circle of light across the table. And the room around you, the room you're sitting in right now, with its own walls and its own warmth and its own quiet, is exactly as it should be. There's nothing you need to figure out before morning. Nothing you need to hold on to. Nothing that requires your attention in this moment. You've already held something remarkable tonight. The quiet fact that the universe is mostly made of mystery. That we live in a cosmos where 95% of the recipe is written in ink we can't yet see. Where the scaffolding is invisible. Where the push is patient. Where the frame holds even though we've never touched it directly. And that mystery, that vast, quiet, patient mystery, isn't something to solve before you sleep. It's something to rest inside of. Because mystery, it turns out, is a very restful thing to hold. It doesn't ask anything of you. It doesn't demand answers or action or understanding. It simply is, like the warmth of the room, like the weight of the blanket, like the steady rhythm of your own breathing. The lamp is dimming now. The book is resting. The room is warm and still. And you, here, now, in this small circle of light, are part of the 5% that glows. The 5% that breathes and wanders and rests. And that's enough. That's more than enough. Good night. The lamp is on again. The same warm circle on the table. The same quiet settling around it. Familiar now. The book is where we left it. Not moved, not closed, not forgotten. Just resting, patient. The way a book does when you've been thinking about it, and you know you'll return. Maybe you've thought about it since last time. The recipe we read together, the proportions that make up everything. 5 pages written in ink we recognized. 27 more we could make out if we looked carefully. And 95 pages where the words seem to be missing. The paper unmarked, blank to our eyes, but somehow not empty. We noticed something else that night. Something underneath the words, behind them. The shelves where the book sits, the frame that holds those shelves in place without bending, without sagging, even with all that weight resting on them. The studs and beams running through the walls, invisible beneath the plaster, hidden behind the paint, but undeniably there, real. The structure that keeps everything from collapsing. You've probably felt that in a house before. The solidity beneath your feet. The way a wall feels stable when you lean against it, even though you can't see the wooden frame inside. You trust it. You rest your weight on it, and it holds. Tonight, we're going to look more closely at that frame. Not by tearing anything apart, not by pulling the plaster off the wall to expose what's underneath, not by breaking through to see the beams, just by noticing, carefully and patiently, the signs that it's there, the clues that tell us something is holding everything in place, even when we can't see it directly. The lamp casts its steady light across the table. The book is open to where we left off, the chapter on the scaffolding, the invisible architecture. The pages are crisp and waiting. The room is warm, and we have time. We have all the time we need to turn these pages slowly, to let each one settle before moving to the next. Here's the question that sits at the heart of this chapter. How do we know the scaffolding is there if we've never seen it directly? How do scientists, how do you and I, come to understand something we cannot photograph, cannot touch, cannot observe with our eyes? How do we become confident that the frame exists, that it's real, that it holds the weight we think it does? The answer is the same way you might notice a door frame is slightly crooked and realize the house has settled over time. The door still closes, the frame still stands, but there's a tilt now, a lean, and that tilt tells you something about the foundation beneath the floor, about shifts you never witnessed, but that left evidence behind. Or the way you might feel a draft, a thin current of cool air moving through a room, and know there's a gap somewhere in the wall, even though you can't see it. The draft itself is the evidence. It points to something invisible, a crack, a space, an opening between boards. Or the way you might hear a floor creak in a particular spot and know, without looking, that there's a joist beneath that board. The structure is hidden under carpet and wood, but the sound tells you it's there. The house speaks if you listen. You pay attention. You watch how things behave. You notice patterns. You piece together a picture from clues, not from direct observation. Scientists are patient readers. They don't rush to conclusions. They don't leap from one observation to a grand theory and call it finished. They observe, measure, compare. They notice clues in the way galaxies move, in the way light bends, in the patterns written into the oldest light in the universe. And slowly, over decades, those clues begin to tell the same story. Different voices, different methods, same story. Tonight, we have three main kinds of evidence. Three different ways of noticing the same thing. We'll take them one at a time, like turning pages. No rush, no urgency, just the quiet satisfaction of watching separate pieces fit together into a single, coherent picture. We're not going to pull the plaster off the wall. We're going to run our fingers along the surface and feel where the beams are. We're going to notice how the shelf stays level, even when you add weight to one side. Something is distributing that weight. Something is bearing the load. We're going to see how the house holds. The first clue came from watching how galaxies spin. The way the outer edges move, faster than they should, faster than we expected, faster than the visible mass alone could explain. Let's turn to that page. In our solar system, the planets farther from the Sun orbit more slowly than the planets closer in. Mercury, hugging tight to the Sun's warmth, completes its orbit in just 88 Earth days. It races around the Sun, fast and close, pulled hard by gravity. Neptune, out in the cold dark, takes 165 Earth years to make the same journey. It crawls through its orbit, distant and slow, barely tugged by the Sun's distant pull. Between them, the other planets follow the same pattern. Venus faster than Earth, Earth faster than Mars, Mars faster than Jupiter, each one a little slower than the one before as the distance grows. This isn't arbitrary or random. It follows directly from gravity, from the mathematics Isaac Newton wrote down centuries ago. The Sun's gravity pulls hardest on Mercury, gently on Neptune. Less gravitational pull means a slower orbit, a gentler curve through space. If you could somehow move Neptune closer to the Sun without changing anything else, it would speed up, forced into a tighter, faster path. If you pushed Mercury outward, away from the Sun's pull, it would slow down, settling into a longer, more leisurely orbit. This pattern, fast near the center, slow at the edges, is what we'd expect anywhere gravity works the same way. It's a universal principle, as reliable as the sunrise. So when astronomers turned their telescopes to galaxies, vast collections of billions of stars, bound together by gravity, they expected to see the same pattern there. Most of a galaxy's visible light comes from its bright center, where stars are packed densely together, crowding close like people in a city center. The edges are dim, sparse, scattered. The light thins out as you move away from the core. Light marks where the mass is. That's been true throughout astronomy. Bright means massive, dim means sparse. And if most of the mass is concentrated in the center, then stars at the outer edges should be orbiting slowly, gently, like Neptune crawling through its long year. Think of it like a book on the table in front of us. The pages are heavier near the spine, where the binding holds them tight, where the paper is layered thick. The margins are lighter, thinner, easier to lift. The weight is concentrated where the structure is. If you were to spin the book, the spine would pull harder than the edges. That's what we expected to find in galaxies. That's what the mathematics predicted, what decades of work with Newton's equations told us to look for. Fast rotation near the bright center, where the mass is. Slow rotation at the dim edges, where the mass thins out and the gravitational pull weakens. But when scientists finally developed the tools to measure the speeds carefully, out at those dim edges where the light fades into darkness, that's not what they found. In the late 1960s and through the 1970s, two astronomers, Vera Rubin and W. Kent Ford Jr., began measuring how fast stars were moving at the outer edges of spiral galaxies. This was technically difficult. The edges of galaxies are dim, very dim. The stars out there are sparse, and their light faint, barely reaching us across the vast distances of space. Previous instruments couldn't gather enough light to measure their speeds reliably. The signal was too weak, the data too noisy. But Kent Ford had built something new, an image tube spectrograph that could amplify faint light, turning whispers into measurable signals. It made it possible to measure the speeds of stars in regions no one had been able to study before. The far edges, the dim outskirts, the places where galaxies fade into the dark. It was patient, careful engineering. Not dramatic, not flashy, just effective. The kind of work that takes years to perfect, that solves one technical problem after another, until finally, quietly, it works. In 1970, Rubin and Ford published a study of the Andromeda Galaxy, M31, the nearest large spiral galaxy to our own. They measured the speeds of stars far from the center, out where the visible light fades into darkness, where you'd expect everything to be moving slowly. The outer stars weren't slowing down. They were moving at about the same speed as stars near the center, roughly 200 to 250 kilometers per second. Fast. As fast as the inner stars, as fast as stars surrounded by all that concentrated light and mass. The rotation curve, as it's called, was flat, not declining, not tapering off the way Newton's gravity said it should, just flat, level, as if something unseen were holding those distant stars in a faster orbit than the visible mass could account for. It was unexpected, puzzling. But one galaxy might be an anomaly, a quirk, an exception to the rule. So they kept measuring, galaxy after galaxy, patiently, methodically. In 1980, Rubin and Ford published a comprehensive study of 21 spiral galaxies. They found the same pattern in every single one: flat rotation curves, outer stars moving as fast as inner stars, even though most of the visible light, most of what we assume to be the mass, was concentrated in the center. The data was too consistent to dismiss, too clear across too many galaxies. Vera Rubin turned what had been a fringe curiosity, a strange observation noted by a few, into undeniable evidence. The numbers didn't match the expectations. Something was missing from the picture. It was as if every book on the shelf weighed the same at the margin as it did near the spine. As if something unseen were adding weight to the edges, holding them steady, keeping them from sagging under their own lightness. The lamp still glows on the table. The book is still here, the pages turning under our attention. And we've just read the first clue. Galaxies don't spin the way they should, if only visible matter is present. The flat rotation curves mean something specific. There is much more mass in a galaxy than the stars and gas we can see. Roughly 5 to 10 times more. But that invisible mass isn't distributed the way the visible matter is. The stars and glowing gas we photograph are concentrated in a flat disk at the center. The beautiful spiral arms you see in pictures, bright and photogenic, the iconic image we think of when we picture a galaxy. That bright disk might stretch 50,000 or 100,000 light years across. A vast pinwheel of light spinning in the darkness. But the invisible mass forms something different. A vast, roughly spherical halo that surrounds the visible galaxy and extends far beyond it. It reaches perhaps 100,000 to 300,000 light years from the center, 2 or 3 times the diameter of the visible disk. The bright spiral, the part we photograph and study and marvel at, is just a small circle sitting inside this enormous invisible sphere. Picture the lamp on the table again. The light makes a bright circle on the surface, clear, well-defined, easy to see. The edges are sharp. You can point to where the light stops. But the room extends well beyond what the lamp illuminates. The walls are out there in the darkness, a few feet away, maybe 10 feet, maybe more. The corners are dim. The far edge of the room is invisible from here. But the room doesn't end where the light does. The frame of the house doesn't stop at the edge of the lamplight. It continues, hidden, holding the structure even in the darkness. The visible galaxy is the lamplight. The dark matter halo is the room. This was the first clue. The first page turned. Galaxies spin in a way that only makes sense if most of their mass is invisible, spread in a vast sphere around the bright center we've been photographing for more than a century. The rotation curves told us this. The numbers demanded it. And once scientists knew to look for this hidden mass, once they understood what the rotation curves were telling them, they found it again, in a completely different way, using completely different physics, looking at a completely different phenomenon. Let's turn that page now. Light travels in straight lines. That's the simple version, the version we learn first, and it's mostly true. But there's a subtlety. Light also responds to gravity, not because light has mass the way a planet or a star does, but because gravity curves the space light travels through. A massive object, a star, a galaxy, a cluster of galaxies, bends the space around it the way a heavy book might bend a soft surface. And when light passes through that bent space, its path curves. It follows the curve of space itself. Imagine looking through the window of the house, and the view outside is gently warped. Not because the landscape has changed, but because the glass itself is curved. Something heavy resting on the windowsill has bent the glass. The tree in the yard looks stretched, the fence looks curved, but the distortion isn't in the tree or the fence. It's in the glass you're looking through. The weight on the sill has changed how you see the world beyond. That's what massive objects do to space. They bend it, and light, traveling through that bent space, bends with it. Albert Einstein predicted this in 1915 in his theory of general relativity. He described gravity not as a force pulling on objects, but as a curvature in the fabric of space and time itself. Mass curves space. Light follows that curve. In 1919, Arthur Eddington confirmed it. He observed how starlight bent as it passed near the sun during a solar eclipse, when the sun's glare was blocked and the stars near its edge became visible. The deflection was tiny, barely noticeable, a fraction of a degree. But it was there, exactly where Einstein's equations said it should be. The stars appeared slightly shifted from their true positions because the sun's mass had bent the space between them and us. Now scale that up. Instead of a single star bending light a little, imagine a massive cluster of galaxies, hundreds of galaxies bound together by gravity, occupying a region millions of light years across, containing more mass than 1,000,000,000,000 suns. An object that massive bends space significantly, dramatically. And when light from a distant galaxy passes near that cluster on its way to us, the light's path curves, sometimes gently, sometimes sharply. From Earth we see something strange. The background galaxy appears stretched, smeared, distorted. Sometimes it's bent into an arc, a graceful curve of light wrapped partway around the cluster. Sometimes, if the alignment is just right, the light bends all the way around the cluster in a complete circle. An Einstein ring, a perfect halo of light from a single distant source, bent into a circle by the gravity of the foreground mass. This is called gravitational lensing. The foreground cluster acts as a lens, bending and magnifying the light from galaxies behind it. And here's what makes it useful. The amount of bending depends on the mass of the lens. More mass means more bending, more curvature in space. By measuring how much the background light is distorted, by studying the shapes of the arcs, the positions of the rings, the degree of the stretching, astronomers can calculate how much mass the foreground cluster contains. They can weigh the cluster. It's a scale, a way to measure something you can't touch. The book on the table casts a shadow on the surface. The shadow is longer in the evening, shorter at noon, shaped by the angle of the light. By looking at the shadow's shape and size, you can infer the shape and size of the book, the angle of the light, even if you never pick the book up or turn on a brighter lamp. The shadow is evidence. It tells you what's there. When When astronomers used the Hubble Space Telescope to photograph distant galaxy clusters, they found exactly this kind of distortion everywhere they looked. Able 2218, Able 370. These are massive clusters, each containing hundreds of galaxies, bound together by gravity into a single structure millions of light years across. In the Hubble images, you can see them clearly. The foreground galaxies, bright and sharp, resolved into individual points of light. But you can also see something else. Arcs, streaks of light that curve around the cluster in graceful, sweeping paths. These are background galaxies, galaxies far behind the cluster, so distant they'd normally be too faint to see clearly. But the cluster's gravity has bent their light, magnified it, brought it into focus. The light has been stretched and curved into these beautiful arcs. The arcs are stunning, almost artistic, like brushstrokes of light painted across the darkness. Some are thin and delicate, barely there wisps. Others are thick and bright, nearly complete semicircles. Each one is a different galaxy, distorted by the same lens, each one bent by the same invisible mass. But they're not just beautiful, they're also a measurement. Each arc is a data point. Each curve tells you something about the mass distribution in the foreground cluster. By studying the arc's shapes, how curved they are, how stretched, how far they wrap around the cluster, astronomers can map where the mass is. They can create a gravitational map of the cluster, a picture not of the light, but of the mass that bends the light. It's like tracing the contours of a valley by watching how water flows through it. The water's path reveals the shape of the land. And when they did this, when they created these gravitational maps, they found the same pattern Vera Rubin had found with rotation curves decades earlier. The clusters contain far more mass than the visible galaxies account for. Not twice as much, not 3 times, hundreds of times more. The mass is there. The bending confirms it. The arcs confirm it further. But most of it isn't glowing. It's not in stars, not in gas, not in anything we can photograph directly. It's invisible. In some cases, the alignment is perfect. The foreground cluster, the background galaxy, and Earth all line up precisely, exactly along the same line of sight. When that happens, the background galaxy's light bends into a complete circle around the cluster, an Einstein ring, a ring of light marking where space curves most sharply. One example is the cosmic horseshoe, a nearly complete Einstein ring discovered around a galaxy cluster designated LRG 3-757. The ring is almost closed, almost a perfect circle, with just a small gap where the alignment isn't quite exact. It's beautiful, but more importantly, it's precise. The ring isn't decorative, it's data. It provides an exact measurement of the cluster's mass, including all the mass that isn't emitting light. The ring maps the curvature of space, and that curvature is determined by mass. All the mass, visible and invisible. The lamp still glows steadily on the table. The room is still warm. The book is still here, pages turning slowly under our hands. And we've just read the second clue. Light bends around clusters in a way that only makes sense if most of the mass bending that light is invisible, undetected by our telescopes, present only in the curvature of space itself. 2 different methods now, 2 different decades, 2 different kinds of measurement. Rotation curves in the 1970s and 80s, gravitational lensing in the 1990s and 2000s, both using different physics, different mathematics, different observations, both pointing to the same conclusion. The frame is there. Let's set these 2 pages down for a moment. 2 pieces of evidence, 2 separate discoveries, 2 independent confirmations. The rotation curves showed us the mass is there. The lensing showed us where it is. Different tools, same result. The lamp burns steady, the book rests open, and there's a third clue waiting, the oldest one, written into the most ancient light in the universe. The oldest light we can observe comes from about 380,000 years after the beginning. Before that moment, the universe was too hot and dense for light to travel freely. Electrons and protons were unbound, moving separately, and photons, particles of light, couldn't move more than a short distance before scattering off a free electron. The universe was opaque, foggy with energy. But as the universe expanded, it cooled, and at a specific moment, when the temperature dropped just enough, electrons and protons combined into neutral hydrogen atoms. Suddenly, the electrons were bound. The photons had nothing to scatter off. Light could travel freely for the first time. The universe became transparent, and the light that was released at that moment, the afterglow of that transition, the photons that suddenly found themselves free to move, has been traveling through space ever since. The universe has expanded while that light traveled, and the expansion has stretched the light, cooling it, shifting it from visible light to infrared to microwaves. Today, that light fills the entire sky. It comes from every direction, faint and cold, just a few degrees above absolute zero. We call it the cosmic microwave background, the CMB, a relic of the universe's earliest observable moments, a snapshot of what the cosmos looked like when it was 380,000 years old. And here's what makes it remarkable. The CMB isn't perfectly smooth. It's almost smooth. Smooth to an extraordinary degree, in fact, which tells us the early universe was remarkably uniform. But it has tiny fluctuations, hot spots and cold spots, temperature variations of about 1 part in 100,000. Those fluctuations aren't random. They aren't noise. They represent sound waves, pressure waves, that rippled through the hot, dense matter in the early universe before the light was released. Regions that were slightly denser compressed the matter around them. Regions that were slightly less dense allowed the matter to expand. The matter vibrated, it oscillated. The sound waves left an imprint, a pattern frozen into the light at the moment the universe became transparent. And by measuring that pattern carefully, by studying those tiny temperature variations across the sky, astronomers can learn about the conditions in the early universe. They can measure how much ordinary matter was there, how much dark matter, how the two interacted, how the sound waves moved through them. It's like the pattern of lamplight on the wall, where the shadows fall, how they overlap, how the brightness varies. That pattern depends on the shape of the room and where the walls are. Even if you can't see the walls directly, the light pattern tells you they're there. The fluctuations are evidence. They point to structure. Or think of it like holding a book and noticing that some pages are thicker than others. You can't see what's written on those pages without opening them, but you can feel the difference. The pattern tells you something about what's inside. When scientists analyze the CMB, they look at what's called the angular power spectrum. It's a graph. On one axis, the size of the temperature fluctuations. Are we looking at large patches of sky or small patches? On the other axis, the strength of the fluctuations. How much do the hot and cold spots vary? The graph has peaks, several of them. The peaks represent the sound waves, the oscillations in the early universe. The first peak represents the largest sound waves, the ones that had completed half an oscillation by the time the light was released. The second peak represents waves that had completed a full oscillation. The third peak, smaller waves still. And here's the key. The ratio of the peak heights depends on how much dark matter there was compared to ordinary matter. Ordinary matter. Atoms, protons, neutrons, the matter we're made of, interacts with light. It feels the pressure of photons. Dark matter doesn't. It doesn't interact with light at all. So the two kinds of matter moved differently in the early universe. They oscillated differently, and that difference is written into the peak heights. If there were no dark matter, the peaks would have a different pattern, a different ratio. If there were too much, the pattern would shift again. The observed pattern, the one we actually measure in the sky, matches only one scenario. The early universe contained roughly 5 times as much dark matter as ordinary matter. This isn't guesswork. The data comes from the Planck satellite, which observed the CMB from 2009 to 2013 and published its final results in 2018. The measurements are extraordinarily precise, refined over years of observations. The Planck data gives us numbers. About 26.8% of the universe is dark matter. About 4.9% is ordinary matter, the atoms that make stars and planets and people. The rest, about 68.3%, is something else entirely, which we'll come back to in future chapters. Back here by the lamp, those percentages are just quiet marks on a page. Numbers in ink. What matters is this: 3 different ways of looking, rotation curves, gravitational lensing, and now the cosmic microwave background. 3 different methods, 3 different decades, 3 different kinds of physics. And all 3 give answers that agree. These numbers fit a wide array of observations, not just the CMB, but also the large-scale structure of the universe, the way galaxies cluster together in filaments and voids, the way matter distributes itself over billions of light years. The framework is consistent. It holds across scales, from individual galaxies to the entire observable universe. The lamp casts its steady glow on the table. The book remains open. The page is still and patient. And we've just read the 3rd clue. The oldest light in the universe carries a pattern that only makes sense if the early universe was filled with invisible matter, distributed in a specific ratio to the matter we can see. The pattern of light on the wall reveals the shape of the room. 3 independent lines of evidence now. 3 different methods, developed in different decades, by different teams, using different physics, all agreeing, all pointing to the same invisible structure. But there's one more page to turn, one more kind of observation, and this one is perhaps the most direct. In 2006, astronomers published observations of a system called the Bullet Cluster, officially designated 1E0657-56. It's not a single cluster. It's 2 galaxy clusters that pass through each other, moving at tremendous speed. When that happened, something remarkable occurred. something that separated structure from substance in a way we could measure directly. The galaxies themselves, individual galaxies, each containing billions of stars, are mostly empty space. The distances between stars are vast, so when the two clusters passed through each other, the galaxies slipped past one another relatively unscathed. Like two sparse forests interpenetrating, tree branches passing through empty space between trees. But the hot gas between the galaxies, the intergalactic gas that fills the space between stars, met and tangled together, slowing due to friction. Gas clouds meet and tangle, particles interact. The atoms in one cloud bump into atoms in the other cloud, and friction slows them both down. The gas couldn't pass through cleanly. It stayed behind. It's as if two rooms in the house had merged for a moment, and the furniture in each room tangled and stopped in the middle where they met. Chairs caught on tables, carpets bunched together. The furniture couldn't pass through. It accumulated. The Chandra X-ray Observatory mapped the hot gas. In the X-ray images, which detect hot, energetic matter, you can see two clumps of gas left behind in the middle where the two clusters met. The gas is glowing, visible, measurable. You can point to it and say, that's where the ordinary matter is. That's where the atoms are. But when astronomers used gravitational lensing to map where the mass is, where the gravity is strong enough to bend background light, they found something unexpected. Most of the mass didn't stay with the gas. Most of the mass kept moving. It separated from the gas. It traveled outward with the galaxies, continuing through the collision site, while the gas stayed behind. The mass and the visible matter had separated. They were no longer in the same place. You could point to the gas and say, there's the visible matter. And you could point to the lensing map and say, there's where the mass is. And they didn't match. The mass was displaced from the matter. The frame and the furniture had separated. The furniture, the gas, the atoms, the stuff we can detect directly, stayed where the friction held it, tangled in the middle. The frame, the invisible structure, the dark matter, kept moving. It passed right through. This is difficult to explain with modified gravity. If gravity itself was simply behaving differently at these scales, if there were no invisible mass, just a change in how gravity worked, then the gravitational pull should still be centered on the visible matter, on the gas. Gravity should pull from where matter is, but it's not. The gravity is displaced from the gas. It's traveling with something we can't see, something that passed through while the gas stayed behind. It's hard to move the location of gravity without moving mass. The simplest explanation, the one that fits the observations most naturally, is that most of the mass in those clusters is invisible, doesn't interact with normal matter the way gas does, doesn't feel friction, and simply passed through while the gas stayed behind. The invisible structure is made of something physical, something with mass and gravity. It's not just a modification of the laws, it's matter. We can't see it, but it's there, and it behaves differently than the matter we can see. The lamp still glows on the table, steady and warm. The book still rests where we left it, pages open. And we've just read the fourth clue. Two galaxy clusters that passed through each other, leaving the gas behind, while the invisible structure kept moving forward. 4 pages turned tonight, each written in different ink, by different hands, in different decades, each using different tools, different mathematics, different observations, and they all describe the same frame behind the same walls. We can close this chapter gently now. The evidence is gathered, the pages are turned, 4 separate ways of looking, 4 separate confirmations. Let them rest on the table for a moment, while we ask one more quiet question before the night is done. The evidence for dark matter is among the strongest cases in modern astrophysics. 4 independent methods. Rotation curves, measured patiently in the 1970s and 80s by Vera Rubin and others. Gravitational lensing, observed in the 1990s and refined with Hubble, mapping mass through bent light. The cosmic microwave background, mapped in exquisite detail by the Planck satellite, revealing the proportions of matter in the early universe. And the bullet cluster, 2 clusters passing through each other while mass and visible matter separated. 4 different kinds of observations, different physics, different tools, different mathematics, developed over decades by different teams in different countries, using different telescopes and instruments, all agreeing, all pointing to the same conclusion. This is not a guess. This is not a gap in our understanding that we've filled with a placeholder name, a label for our ignorance. The scaffolding is there. Every measurement confirms it. The rotation curves wouldn't make sense without it. The outer stars would slow down, but they don't. The light wouldn't bend the way it does. The arcs would be smaller, dimmer, but they're not. The CMB wouldn't have the pattern it has. The peak ratios would be wrong, but they're not. The bullet cluster wouldn't have behaved the way it did. The mass would have stayed with the gas, but it didn't. We know it exists. We know how much of it there is. Roughly 5 times as much as ordinary matter, give or take. We know what it does. It holds galaxies together, shapes the large-scale structure of the universe, influenced the formation of the first galaxies after the Big Bang. We have measured its effects in precise, repeatable ways, multiple independent confirmations. But, and this is important to say clearly, honestly, we still don't know what it's made of. We haven't identified the material. We haven't caught one in a detector. We haven't held it or seen it interact with anything we can observe directly except through gravity. We've confirmed the frame is real. We've measured its weight, its distribution, its influence. We've mapped where it runs behind the walls, but we haven't yet touched the material itself, haven't identified whether it's wood, steel, or something we don't have a name for yet. Evidence for existence is not the same as identification. And that distinction matters. It's an important line. We can be confident the scaffolding is there and still be uncertain what it's built from. Not everyone agrees that the invisible scaffolding is the right way to read the evidence. Some scientists have proposed a different interpretation. Maybe there is no invisible mass at all. Maybe gravity itself works differently than Newton and Einstein described, especially at the very low accelerations found at the edges of galaxies, where the gravitational pull is weak and gentle, barely tugging on the outer stars. This idea, proposed by Mordechai Milgram in 1983, is called modified Newtonian dynamics, often shortened to MOND. MOND is clever, it's thoughtful. For many individual galaxies, it predicts the rotation curves remarkably well, without needing any dark matter at all. It adjusts the mathematics of gravity at low accelerations, and the flat rotation curves fall out naturally from the equations. It's elegant in its own way, mathematically simple. But Mond struggles at larger scales. It has difficulty fitting the cosmic microwave background power spectrum. The peaks don't come out right. It doesn't naturally explain the bullet cluster, why the gravitational pull would be displaced from the visible gas when the two clusters passed through each other. It has trouble accounting for the behavior of galaxy clusters in general, and with the large-scale structure of the universe, the way galaxies cluster across billions of light years. The mainstream view, as it stands today, is that dark matter provides a more complete explanation. It fits more of the evidence across more scales, from individual galaxies to the entire observable universe. But that doesn't mean Mond is foolish or unscientific. It's a genuine scientific question, asked with care, by thoughtful people who are trying to understand the same observations we all see. Think of it as two ways of reading the same page, two interpretations of the same text. One interpretation fits more of the words, accounts for more of the sentences. The other interpretation is narrower, fits fewer observations. But the narrower interpretation isn't nonsense. It's not wrong in some obvious way. It's just less complete. The lamp still glows steadily on the table. The book still rests, open and patient. And we've acknowledged both what we know, the evidence is strong, and the honest boundaries of that knowledge. We know the scaffolding exists. We don't yet know what it's made of. And there are still questions being asked, still alternative ways of reading the evidence. Tonight was about evidence, about how we know the frame is there. It wasn't about what the frame is made of. That's a different question, a question with candidates and experiments and ongoing searches. Particle detectors deep underground, satellites looking for specific signals, theories about what dark matter might be, not just that it exists, but what it's composed of, how it behaves, why it doesn't interact with light. That's the next chapter in the book, resting on the shelf, ready whenever you'd like to turn to it. But this chapter, the chapter on evidence, is complete. The question we set out to answer at the beginning of the evening was, how do we know the scaffolding exists if we've never seen it directly? And we've answered that question by watching how things move, by observing how light bends, by reading the patterns written into the oldest light, patterns that only make sense if invisible matter was present in the early universe, and by noticing what happens when structure and substance separate, when the frame and the furniture move independently. The chapter on identity, what the dark matter is, what particles it might be made of, how we might detect it directly, is there on the shelf, resting, waiting. No rush, no urgency. We don't need to pick a side or solve a mystery tonight. We don't need to identify the material or choose between competing theories. The evidence is here. The frame holds. It's real. It exists. And that quiet certainty, the kind built from patience, from multiple independent observations, from decades of careful work, is a good thing to carry into the dark. Tonight we looked at how scientists discovered the invisible scaffolding. We watched galaxies spinning faster than they should at their edges, their outer stars keeping pace with the inner ones, orbiting at speeds that only make sense if something unseen is holding them. We saw light bending around massive clusters, warping and stretching into beautiful arcs, revealing far more mass than any photograph could capture. We read the pattern in the oldest light in the universe, a pattern of hot and cold spots that only makes sense if the early cosmos was filled with invisible matter in a specific proportion to visible matter. And we observed two galaxy clusters that passed through each other, leaving the glowing gas behind, while the invisible structure kept moving forward, separating mass from matter in a way we could measure directly. 4 clues, 4 independent methods, 4 different kinds of observation, each one carefully measured over years or decades, each one pointing to the same quiet conclusion. The scaffolding is real. Last time we noticed the book had blank pages, most of the pages in fact. We acknowledged that we couldn't read them, not yet, but that they were there. The pages weren't missing. They were just written in ink we couldn't see. Tonight we examined the evidence that something is written on those blank pages. We didn't read the words themselves. We didn't identify what they say, what particles they describe, what material they're made of. But we confirmed, carefully and patiently, that the pages aren't empty, that the frame exists, that the structure holds. Next time, if you'd like, we'll look at the candidates, the possibilities for what the scaffolding might be made of, what particles might compose it, what the frame is built from, the search for the material itself, the experiments, the theories, the ongoing hunt for direct detection. But that's a chapter for another night. The bookmark rests between these pages. The chapter on how we know is behind us now, complete and settled. The chapter on what it might be is ahead, whenever you're ready. Return to the room for a moment. The lamp still glows, though its light is softer now, gentler. The book still rests on the table, open to the page we just finished, the words settling into place. The air is still. The night is quiet and deep. Tonight we held something rare, the knowledge that we can understand things we cannot see, not by touching them, not by photographing them, not by holding them up to the light and examining them directly, but by paying attention to how things move, how light bends, how patterns form in the oldest light, how the frame and the furniture separate when they're tested. That kind of knowledge is patient. It doesn't hurry. It doesn't demand anything tonight. It doesn't ask you to solve anything, or decide anything, or worry about what comes next. It's knowledge built slowly, over decades, by many hands, many eyes, many careful measurements. It's solid. It holds. The frame is there, behind the walls, as it has always been, supporting the structure, holding everything in place, keeping the house from collapsing under its own weight. You've known this all along, haven't you? The way you know a house has studs, even if you've never looked inside the walls. The way you trust a floor to hold your weight, even though you can't see the joists beneath the boards. Tonight, you simply noticed the evidence. You saw how the clues fit together. You read the pages that describe the frame, and you can rest against that frame now. You can lean your weight on it. It holds. It's held for billions of years, through the formation of galaxies, through the clustering of matter, through the expansion of space itself. It will hold tonight. It will hold tomorrow. The lamp is dimming now, its glow fading to a warm ember. The book remains where we left it, resting on the table, pages open but still. The words are quiet. The night is deep and safe. The frame holds. You can rest against it. Good night. We're back in the quiet room, you and I. The lamp is still lit, just as we left it. The same warm circle of light on the table, the same gentle glow reaching into the corners. There's something comforting about returning to a space that hasn't changed, finding it exactly as you remember. The chair is still pulled close. The book is still open on the table between us. The air is still. It's good to be back here. In our first evening together, we noticed something strange. The universe, as we tried to add up its contents, didn't balance. The numbers refused to close. There were blank pages in the book where we expected text, and no matter how carefully we counted, the visible matter fell short. In our second evening, we sat with that strangeness and confirmed it. Galaxy rotation curves, gravitational lensing, the way clusters of galaxies hold together against their own motion. Multiple independent observations, each arrived at through different methods, all pointing to the same conclusion. Something is written on those pages. We just can't see the ink. The evidence is solid. The mystery is real. And tonight, we turn to a different question. Not what the evidence shows, but what the answer might be. Imagine we've stood up from the table and walked over to a shelf in the library. Not a distant room, just across the hall. The lamp's light reaches this far, soft and steady. On the shelf sit several volumes. Each one proposes a different answer to the question we've been holding. Each suggests what that invisible writing might say, what form the missing matter might take. Some of these books are thick and well-worn, with cracked spines and pages that fall open easily to familiar passages. Others are slimmer, with notes still penciled in the margins, ideas still being tested. None has been confirmed as the right answer, but none has been ruled out entirely either. We're not here tonight to pick a winner. That's not the kind of evening this is. We're here to understand what's on the shelf, to pick up each volume, look at it carefully, and set it back down, to see why each earned its place here, and what would need to happen for us to know which one is correct. Think of it as browsing, not deciding. There's a particular freedom in that, isn't there? When you browse a shelf without pressure, without needing to choose, you can let each book be what it is. You can appreciate the craftsmanship, the argument, the way ideas connect, without forcing a conclusion. You're not dismissing anything. You're not committing to anything. You're just looking, carefully and openly, at what's there. That's the spirit we'll hold tonight. The simplest framework goes like this. If something has mass but doesn't emit light or absorb it, if it interacts with gravity but barely touches anything else, then it's probably made of matter we haven't directly detected yet. New particles, in other words. Particles that exist outside the catalogue we've built so far. This is where the term dark matter becomes useful shorthand. Not darkness as mood or threat, but darkness as description. Matter that doesn't shine, matter that passes through telescopes without leaving a trace, that holds galaxies together through gravity alone. Most of the candidates we'll look at tonight fall into this category. Particles with different masses, different behaviors, different ways they might have formed in the early universe. Each one is a hypothesis built on mathematics, on observational constraints, on the way physics allows matter to behave. But before we walk along the shelf and pick up the first book, let's set one thing down clearly. These are not wild guesses. Each candidate emerged because it solved a problem, or fit a pattern, or appeared naturally in a larger theoretical framework. They're here because they're plausible, not because they're entertaining. Plausibility in physics is a narrow gate. The universe has rules. Any candidate has to pass through those rules without breaking them, and the rules are strict. So let's begin. Let's reach for the first volume, the one that's been studied longest, the one that for decades seemed most likely to hold the answer we need. The first book we pick up is thick, heavy in the hand. The spine is labelled WIMPs, weakly interacting massive particles. The name is precise, almost technical. These would be particles with mass, substantial mass, enough to account for the gravitational effects we observe in galaxies and clusters. And they would interact weakly, meaning they'd pass through ordinary matter almost without touching it. Not completely invisible to detection, but close. Very close. The weakly here refers to something specific. It's not a casual description. It refers to the weak nuclear force, one of the four fundamental forces in physics. The weak force is responsible for certain kinds of radioactive decay. It operates at extraordinarily short ranges, deep inside atomic nuclei, and it governs processes that allow particles to change type. If dark matter particles interact through the weak force, they'd behave somewhat like neutrinos. Neutrinos stream through the Earth by the trillions every second, barely noticing matter is there. They pass through you, through the chair, through the planet, without leaving a mark. WIMPs would do something similar, but they'd carry far more mass. Now here's the part that made WIMPs so compelling for so long. The part that made this book seem like it might hold the answer. The mathematics worked out almost perfectly. In the early universe, when everything was hot and dense, and particles were being created and destroyed constantly, there was a kind of equilibrium. Particles annihilated with their antiparticles, releasing energy, and that energy created new particle pairs, a continuous cycle. But as the universe expanded and cooled, this process slowed. Eventually, the universe became too sparse, too cool, for particles to find their annihilation partners easily. At that point, certain particles froze out. Their density stopped changing. What was left became a relic population, still present today. This is dense material, but the book explains it patiently. Let's stay with it a moment longer. Physicists can calculate how much of a given particle should remain after freeze-out. It depends on the particle's mass and how strongly it interacts. When researchers ran those calculations for particles interacting through the weak force, with masses in a certain range, roughly the mass of 100 protons, the predicted relic abundance matched the observed density of dark matter almost exactly. This wasn't proof, but it was striking, suggestive. It hinted that dark matter might not be exotic at all, might not require entirely new physics. It might be a natural consequence of forces and particles we were already studying for other reasons. Physicists called this coincidence the WIMP miracle. Not a literal miracle, but a mathematical one. A case where the numbers lined up in a way that felt almost too neat to be accidental. Let that sit for a moment. The elegance of it, the way separate pieces of physics, the weak force, the expansion of the universe, the observed density of dark matter, all seem to point toward the same answer. It's the kind of convergence that makes a hypothesis compelling. Not proof, but a kind of internal consistency that suggests you might be on the right track. So researchers built experiments, underground labs, careful detectors, years of patient observation. They set out to find these particles directly. Let's set this book down on the table for a moment and think about what it would take to detect a WIMP. What kind of room you'd need. What kind of listening? If WIMPs are real, they're passing through the earth constantly. Through the walls, through the floor, through you and me as we sit here. Trillions of them, most likely, streaming from every direction, part of the dark matter halo that surrounds the Milky Way. Occasionally, very rarely, one should nudge an ordinary atomic nucleus. Just a gentle push, a transfer of momentum. The nucleus would recoil slightly, releasing a tiny pulse of energy. If you could detect that pulse, you'd have found a WIMP. The challenge is that the signal would be extraordinarily faint. Fainter than almost any other signal you might want to measure. And the noise, from cosmic rays, from natural radioactivity in the surrounding rock, from stray particles of any kind, would drown it out completely. So the experiments went underground, deep underground, into old mines and tunnels, where kilometers of rock overhead filter out most of the cosmic rays. These are quiet rooms, still and patient. Not dramatic spaces, not eerie, just carefully shielded chambers where detectors can sit in stillness, waiting for something real to appear against a nearly silent background. Think about what it means to build a room like that, to go deep into the earth, to shield everything, to cool the detectors to near absolute zero, and then to wait. Years of waiting sometimes, watching for a single flash of light, a single pulse of energy that might be the signal you're looking for. The patience required is extraordinary, not just from the instruments, but from the researchers. To design an experiment that might run for a decade, to check and recheck every possible source of background noise, to sit with the possibility that the signal might never come, and still keep the detector running, still keep recording data, still keep searching. One of the most sensitive is called Lux Zeppelin, or LZ for short. It sits in the Sanford Underground Research Facility in South Dakota, about 1.5 kilometers below the surface. The detector holds 7 tons of liquid xenon, cooled and purified until it's extraordinarily clean, with almost no contamination from natural radioactivity. When a particle interacts with a xenon nucleus, it produces 2 signals, a flash of light and a pulse of ionization. By comparing these 2 signals, researchers can tell what kind of particle caused the interaction. Background radiation leaves one pattern. A WIMP, if it appeared, would leave another. LZ has been running for over 400 live days now, watching, recording, and it's found nothing that can't be explained by known particles. No excess, no signal that points to WIMPs. What it has done is set extraordinarily tight limits. If WIMPs exist in certain mass ranges with certain interaction strengths, LZ should have seen them. It hasn't. So those possibilities are ruled out. There's another detector called XENONNT running in Gran Sasso National Laboratory in Italy. It reached a milestone recently, a kind of threshold physicists both hoped for and dreaded. It detected recoils from solar neutrinos, not dark matter, just ordinary neutrinos from the sun, interacting with the xenon at such low energies that the signal is almost impossible to distinguish from what a WIMP might produce. This is sometimes called the neutrino fog. It means the instrument has become almost too sensitive. Any further improvement will require new techniques, new ways of filtering out the neutrino background to see if there's anything else underneath. Back here by the lamp, we can appreciate what this means. These experiments are pushing the limits of what's possible to measure. They're detecting signals so faint that they're brushing up against fundamental limits. Not limits of technology, but limits set by the universe itself. Let's rest here for a moment, because it's easy to hear no detection after decades of searching and think the search has stalled, that nothing is being learned. But that's not how it works. Every null result teaches us something. It rules out part of the possibility space. If WIMPs exist with this mass and this interaction strength, we should have seen them. We haven't. So they don't exist there. The window narrows. Think of it like testing what the frame of the house is made of. You test for wood, not wood. You test for steel, not steel. Each test teaches you something, even when the answer is no. Even when you haven't found the right material yet. You're narrowing the possibilities, learning what the frame isn't, getting closer to what it might be. This is progress, real progress. It forces theorists to refine their models, to abandon certain parameter ranges, to look elsewhere. It shapes the next generation of experiments, tells them where to search, what sensitivity they'll need to reach. The WIMP hypothesis is not dead, but it's been constrained, bounded, pushed into corners of the parameter space that are harder to reach. If WIMPs exist, they're either lighter than expected or heavier, or they interact even more weakly than the original models suggested. The window is smaller than it used to be, but it's still open. And in the meantime, the experiments continue. New detectors are being built with better sensitivity, different target materials, new techniques for filtering out background noise. The search hasn't stopped. It's adapted. But let's not stay in this one place too long. Let's turn away from the underground labs and look at another volume on the shelf. A different candidate entirely. One that's lighter, stranger, and in some ways more elusive than WIMPs. The second book we pick up feels different. Lighter in the hand, slimmer, but with a kind of elegance to it. The pages are clean, the margins filled with careful annotations. The spine reads, axions. These are not massive particles. They're extraordinarily light. If a WIMP might weigh roughly as much as 100 protons, an axion might weigh a billionth of that, or less, perhaps much less. And yet, if they exist in vast enough numbers, swarms of them, filling space like a fog, they could still account for all the dark matter we observe. Axions weren't invented to solve the dark matter problem. They emerged from something else entirely, a different puzzle buried inside particle physics. Physicists Roberto Pecci and Helen Quinn proposed them in 1977 as a solution to what's called the strong CP problem. The details involve symmetries in the equations that govern the strong nuclear force, the force that holds atomic nuclei together. We don't need to follow that thread tonight. It can rest on the shelf. What matters is that axions appeared naturally as part of the solution. And once theorists realized axions could exist, someone noticed something interesting. If axions were produced in huge quantities in the early universe, they could have the right properties to be dark matter. Not by design, by accident. The axion became a candidate, not because anyone set out to explain dark matter, but because the mathematics led there on its own. Think about what that means. Imagine opening a book expecting one story. A story about nuclear forces, about symmetries in equations, and finding that same book also speaks to an entirely different question you'd been wondering about. A question about the missing mass in galaxies, about the invisible scaffolding holding the universe together. The book wasn't written with that question in mind, but it answers it anyway, or might. There's something deeply appealing about that. A kind of coherence to the universe that you don't expect, but recognize when you see it. It suggests that different pieces of physics might connect in ways we don't initially understand, that solving one puzzle might accidentally illuminate another. But appealing isn't the same as confirmed. The book is elegant, yes, but we don't know yet if it's the right book. Back here by the lamp, we can set this volume down gently and think about what it would take to know. How you'd look for an axion, what kind of signal it would leave, what kind of room you'd need to build. Axions, if they exist, wouldn't interact through the weak force. They'd barely interact with anything, but they would have one fade coupling to electromagnetic fields. This means that in the presence of a strong magnetic field, an axion could occasionally convert into a photon, a particle of light. The conversion rate would be incredibly low, and the photon would be extraordinarily faint, but it would have a very specific frequency, determined by the axion's mass. If you knew where to look, you could tune a detector to that frequency, like tuning a radio to a particular station, listening for a signal that shouldn't be there. Imagine sitting in a quiet room with an old radio, the kind with a dial you turn slowly, manually, listening to the hiss of static as you move through the frequencies. Most stations are silent, empty channels, but occasionally, if you're patient, if you turn the dial carefully enough, a voice emerges from the noise. Faint at first, then clearer. That's the image here. You're sitting in silence, turning the dial slowly, listening for something you're not sure exists. The vast majority of frequencies are empty, just static, just noise. But if the signal is there, if you pass over it, you'll hear it. The patience required is extraordinary. You can't rush through the dial. You have to spend time at each frequency, long enough to be sure that if there's a signal, you'd detect it. And the frequency range is enormous. Thousands upon thousands of stations to check, one by one. This is what axion experiments do. They're not underground labs looking for nuclear recoils. They're cavities, metal chambers filled with powerful magnetic fields, cooled to near absolute zero, listening for faint radio signals emerging from the quantum vacuum. One of the leading experiments is called ADMX, which stands for Axion Dark Matter Experiment. It's located at the University of Washington in Seattle. Over the past several years, ADMX has scanned a frequency range corresponding to axion masses between about 3.3 and 5.4 microelectron volts. It's reached what's called QCD axion sensitivity, meaning it's sensitive enough to detect the type of axion that solves the original strong CP problem, if it exists in that mass range. So far, no signal. But the search continues. ADMX is expanding its range, scanning lower and higher frequencies, one narrow band at a time. There are other experiments too. IAXO, which will search for axions produced in the sun. CASPER, which uses nuclear magnetic resonance techniques to detect axion-induced oscillations. ABRACADABRA, which listens for extremely light axions with a different detection method entirely. Each experiment covers a different part of the parameter space. Each one requires extraordinary precision, careful shielding from electromagnetic noise, patience as the detector tunes slowly through the vast range of possible axion masses. Let that diversity sit for a moment. These aren't all the same experiment repeated. They're different approaches, different techniques, different windows into the same question. Some look for axions passing through the detector. Some look for axions produced in the sun. Some scan high frequencies, some scan low. Together, they're covering the possibility space systematically, carefully, leaving fewer and fewer places for the signal to hide. It's slow work. The frequency range is enormous, and you can't rush through it. You have to spend time at each frequency, long enough to be confident that if there's a signal, you'd see it. Back by the lamp, we can set this down gently. The axion search is ongoing. The methods are advancing, but the answer hasn't come yet. There's something worth noticing about the current moment in dark matter research. Something that's shifted over the past decade or so. For a long time, WIMPs were the default hypothesis, the leading candidate. When physicists talked about dark matter detection, they usually meant WIMP detection. Axions were secondary, interesting, worth pursuing, but not the main focus. That's changed. Today, axions and WIMPs sit on roughly equal footing. Both are leading candidates. Both command significant experimental effort, funding, attention. If you ask a researcher which one they think is more likely, you'll get different answers depending on who you ask. Two things drove this shift. First, the silence from WIMP searches. Decades of increasingly sensitive experiments, all returning null results, pushed physicists to take alternatives more seriously. Not because WIMPs are ruled out, but because the simplest versions of the WIMP hypothesis, the ones that seemed most natural, haven't appeared where we expected them. Second, technological advances. Axion detection requires extraordinary sensitivity to electromagnetic signals. It requires quantum sensors, superconducting cavities, techniques that filter out noise at levels that were barely possible 20 years ago. And those technologies have matured. The instruments that once existed only as proposals, as sketches in research papers, have been built. They're running. What was theoretical is now practical. What was at the edge of feasibility is now routine, or close to it. The tools have finally caught up to the question. So we're in a kind of golden age of axion searches. Multiple experiments, different techniques, scanning different mass ranges, all running in parallel. The parameter space is vast, but it's being covered systematically, carefully, step by step. And yet, as with WIMPs, no confirmed detection. The search continues. Large regions of parameter space remain to be scanned. The answer might be there, waiting. Or it might not. We don't know yet. So we keep both books on the shelf, and we let the experiments continue. Let's turn the page now. Let's look at what else is there, further along the shelf, where the volumes get slimmer and the ideas more speculative. There's another book here, a bit older, with a dog-eared cover and annotations throughout. Most of its chapters have been checked, tested, and set aside, but not all. The spine reads, "Primordial Black Holes." This is a different kind of candidate entirely. Not a new particle, not an extension of the standard model, just black holes. Tiny black holes, formed not from collapsing stars, but from density fluctuations in the first fraction of a second after the Big Bang. The idea is old, dating back to the 1970s. If the early universe had regions that were slightly denser than average, and if those regions were small enough and dense enough, they could have collapsed directly into black holes before the universe had time to smooth them out. These wouldn't be stellar black holes, massive remnants of dead stars. They'd be small, perhaps very small, and if enough of them formed, they could account for the dark matter we observe. No new physics required, just gravity doing what gravity does. It's an elegant idea in some ways, but observations have constrained it heavily. Multiple lines of evidence have ruled out most of the possible mass ranges. If primordial black holes were too light, they would have evaporated by now through Hawking radiation. If they were too heavy, we'd see them through gravitational lensing. When a black hole passes in front of a distant star, its gravity bends the star's light, causing a brief brightening. Surveys have looked for these micro-lensing events and found far fewer than you'd expect if primordial black holes were abundant. The cosmic microwave background also constrains them. If there were too many small black holes in the early universe, they would have affected the formation of the first atoms, leaving a signature in the CMB that we don't observe. And more recently, gravitational wave detectors like LIGO have ruled out certain mass ranges. If there were many black holes with masses between about 10 and 100 times the Sun, they'd be merging frequently enough that we'd see more gravitational wave signals than we do. So most of the parameter space has been checked. Most chapters in this book have been closed, but not all. A narrow window remains. Black holes with masses roughly equivalent to asteroids, between about 10 to the 17th and 10 to the 22nd grams. These would weigh as much as a mountain or a small asteroid, but they'd be tiny in size, roughly the size of a single atom. They're not the favored candidate. Most physicists would bet on WIMPs or axions before primordial black holes. But this mass range hasn't been definitively ruled out, so the idea stays on the shelf, an older book with most pages turned, but a few chapters still unread. And then there are the margin notes, ideas that are more speculative, less developed, but still written down because they're not impossible. Sterile neutrinos, for instance. We know that ordinary neutrinos exist, 3 types of them, part of the standard model. But several experiments over the years have reported anomalies, small excesses or deficits that don't quite fit the 3-flavor picture. One way to explain these anomalies is to add a 4th type, a sterile neutrino, meaning it wouldn't interact through the weak force at all. only through gravity and possibly through very faint mixing with ordinary neutrinos. If sterile neutrinos exist, and if they have the right mass, they could contribute to dark matter. Not all of it, perhaps, but some. The hints aren't conclusive. Different experiments see different things. So this remains a note in the margin, plausible but not confirmed. Or self-interacting dark matter, SIDM. Most models assume dark matter particles pass through each other as easily as they pass through ordinary matter. But what if they don't? What if dark matter has its own interactions, its own internal forces? This could explain certain small-scale puzzles in galaxy structure, cores that appear flatter than simulations predict, for instance. The idea is testable. If self-interactions exist, they should leave signatures in how dark matter distributes itself on small scales. But the evidence so far is ambiguous. So it's another margin note, worth writing down, worth checking, not yet part of the main text. And then there's the dark sector. Not a single particle, but a whole hidden family of them. A parallel set of matter and forces, interacting with each other, but only very weakly with the matter we know. Imagine it like this. Ordinary matter is governed by forces, electromagnetism, the strong and weak nuclear forces. Those forces allow ordinary matter to interact with itself, to form structures, to emit light. What if dark matter has its own forces? Its own version of electromagnetism, perhaps? Its own interactions? This would allow dark matter to have rich internal dynamics, its own structures, even its own analog of chemistry. It's speculative, but it's motivated by a simple observation. If dark matter is 85% of the matter in the universe, why should it be simpler than the matter we see? Why shouldn't it have its own complexity? The challenge is detection. A dark sector would be extraordinarily difficult to observe. You'd have to catch one of those rare moments when it couples faintly to ordinary matter, through gravity or through extremely weak mixing with known particles. A few experiments are looking for such signals, nothing confirmed yet. But the idea remains in the margins, because it's not implausible. These are not the leading candidates. They're possibilities, sketches, ideas that might connect to something real, or might dissolve under closer scrutiny. But they're part of the picture, part of what's being explored. Let's step back from the shelf for a moment. Back to the chair, the table, the steady light. We've looked at several candidates now. WIMPs, axions, primordial black holes, and a handful of more speculative ideas. Each has its own logic, its own experimental program, its own way of fitting into the larger structure of physics. And here's something worth appreciating. The shelf is full. That's not a problem, it's a feature. Science doesn't require that we have only one hypothesis at a time. It works by exploring multiple possibilities in parallel, testing each one against the evidence, letting the data narrow the field. Some ideas will be ruled out, some will survive. One, perhaps, will turn out to be correct, but we don't know which one yet. And that's fine. The process is working as it should. Researchers are searching, carefully and systematically, across a wide range of possibilities. Each null result teaches something. Each new technique opens a part of the parameter space that was previously inaccessible. The search is broad, the search is patient, and the search continues. Let's turn to something else now. Not the candidates themselves, but the nature of searching. what it means to look for something this elusive, and why silence, decades of silence, doesn't mean the search has stalled. We've said this before, but it's worth lingering on, worth really settling into, because the instinct to hear no detection and think nothing learned runs deep. But exclusion is progress. Every time an experiment runs and finds nothing, it's not starting from zero the next time. It's narrowed the field. It's ruled out possibilities. If dark matter interacts in this way, with this strength, in this mass range, we should have seen it. We haven't. So it's not there. Think of it through the house metaphor. You're trying to determine what the frame is made of. You test for wood, not wood. You test for steel, not steel. You test for aluminum, for copper, for various composites. Each test that comes back negative isn't a dead end. It's information. You're learning what the frame isn't. You're narrowing the search space, getting closer to the materials that remain possible. In dark matter searches, this process has been ongoing for decades. Each generation of experiments has pushed the sensitivity deeper, covered more parameter space, tested more hypotheses, and each null result has shaped the next generation, told them where to look, what techniques to develop, what backgrounds to worry about. Lux Zeppelin didn't just fail to find WIMPs. It ruled out huge swathes of the WIMP parameter space with unprecedented precision. ADMX didn't just miss axions. It covered specific frequency ranges with sensitivity high enough to detect the theoretically motivated versions of the particle. And it found they're not there. Not in those ranges, at least. This is how science refines itself. Not through sudden revelations always, but through patient accumulation of constraints. The picture gets sharper even when the answer hasn't arrived yet. And there's something else. Something maybe harder to articulate, but worth trying. When you've ruled out the simplest possibilities, when the easy answers haven't appeared, it means that whatever the truth is, it's more subtle than you expected, more interesting perhaps. Reality is under no obligation to be simple, and when it refuses to be simple, when it hides in corners of the parameter space you didn't initially think to look, that's not failure. That's the universe teaching you something about how it works. Let's think about timelines for a moment, about how long discoveries can take, and what that means for where we are now. The neutrino is a good place to start. Wolfgang Pauli proposed its existence in 1930 to explain certain properties of radioactive decay. The numbers didn't balance without it. Energy seemed to disappear. So Pauli suggested an invisible, nearly massless particle that carried the missing energy away. It made sense mathematically, but detecting it seemed almost impossible. Neutrinos barely interact with matter. They pass through everything. How do you catch something like that? It took 26 years. Clyde Cowan and Frederick Rhines finally detected neutrinos in 1956, using a nuclear reactor as a source and enormous tanks of water as a detector. 26 years from hypothesis to confirmation. Or consider the Higgs boson, predicted in 1964 by multiple theorists, working independently as the mechanism that gives particles mass. The mathematics fit beautifully into the standard model. It explained why certain particles have the masses they do, but detecting it required energies far beyond what any particle accelerator could reach at the time. It took 48 years. The Large Hadron Collider finally found the Higgs in 2012, After decades of technological development, billions of dollars in funding, and the coordinated effort of thousands of physicists, 48 years from prediction to discovery. Or gravitational waves. Einstein predicted them in 1916 as a consequence of general relativity. Ripples in space-time itself, traveling at the speed of light, produced by the acceleration of massive objects. The equations were clear, but the effect seemed impossibly faint. Einstein himself doubted they could ever be measured. It took 99 years. LIGO detected gravitational waves in 2015 from the merger of two black holes more than 1 billion light-years away. 99 years from prediction to confirmation. Let that number sit for a moment. Nearly a century. Generations of physicists working on a problem, building detectors that got closer and closer to the required sensitivity, until finally the instruments were good enough and the signal appeared. Back here by the lamp, we can hold that patiently. 99 years isn't a shortcoming. It's the time the universe needed to reveal itself. The time it took for the question to mature, for the technology to catch up, for the right experiment to be built in the right way. The pattern here isn't that science is slow. It's that the universe doesn't work on our schedule. Some questions take time to answer, not because we're not trying, but because the technology has to catch up to the question. Because the signal is so faint that you need extraordinary precision. Because the right experiment hasn't been built yet, or the right theoretical framework hasn't been developed. But here's the thing. The universe doesn't hide forever. If something is real, if it's there, patient effort eventually finds it. Not always quickly, not always when we'd like, but eventually. Dark matter might take longer still, or it might be detected tomorrow. We don't know, but the search continues, and the methods improve, and the sensitivity deepens, and that's all we can do. Stay patient, keep looking, let the experiments run. So what's ahead? What's on the horizon in terms of experiments and techniques? Lux Zeppelin is still running. It's aiming for 1,000 live days by 2028, which will push its sensitivity even further into the parameter space. If WIMPs are there, in the ranges it's searching, LZ will likely see them. ADMX is continuing to scan new frequency ranges, expanding both upward and downward in axion mass. Each scan takes time, but the coverage is systematic. The parameter space is being explored carefully, methodically, and there's something else. A consortium called XLZD, short for Xenon LZ Darwin. 3 major collaborations, previously building separate detectors, have merged their efforts. They're planning the next generation. A detector with 100 tons of liquid xenon, 10 times larger than anything built so far. If it's funded and constructed, it will push deep into the neutrino fog, searching for signals beneath the background of solar neutrinos. Back by the lamp, these numbers are just marks on a page. What they represent is patience scaled up. Larger detectors, longer observation times, deeper sensitivity. The search continuing, step by careful step. This isn't hype. It's not a promise of imminent discovery. It's just the continuation of the search, with better tools, deeper sensitivity, more systematic coverage of the possibility space. The search continues. That's the phrase to hold here. Not with urgency, not with desperation, just with patience and care. The experiments are running, the data is accumulating, the field is narrowing step by step, and if the answer is there, we'll find it. In time. Let's set this section down gently and turn toward the end of the evening. Back to the table, the book, the quiet room where we started. We've come a long way tonight, you and I. Let's bring the evening to a close by retracing the thread, seeing what we've held. Tonight we looked at the candidates, the possibilities for what dark matter might be. We walked along the shelf, picked up each volume, looked at it carefully. WIMPs, massive particles interacting through the weak force, with a beautiful mathematical coincidence that made them seem natural. Decades of underground searches, extraordinary sensitivity, and so far, silence. The window is narrower than it was, but still open. Axions, extraordinarily light particles proposed to solve a different problem entirely, now standing as a co-leading candidate. Radio cavities, quantum sensors, a golden age of axion searches, and still no confirmed signal. But the parameter space is vast, and the scanning continues. Primordial black holes, an older idea, mostly constrained, but with a narrow window still open. Tiny black holes formed in the first moments after the Big Bang, weighing as much as asteroids but no larger than atoms. And the margin notes. Sterile neutrinos, self-interacting dark matter, the dark sector. More speculative, less developed, but still on the page, because they're not impossible. None confirmed, none fully ruled out. The shelf holds multiple books, and the chapter is still being written. This is not a story with a resolution yet, but it's a story worth following, because the answer, when it comes, will reshape our understanding of the universe at the most fundamental level. Let's pull back for just a moment and trace the thread through the season so far. In our first evening together, we noticed something strange. The universe, when we tried to add up its contents, didn't balance. There were blank pages in the book, pages where we expected text, but saw only emptiness. In our second evening, we sat with that strangeness and confirmed it. Galaxy rotation curves, gravitational lensing, the cosmic microwave background, the way clusters of galaxies hold together, multiple independent lines of evidence, each arrived at through different methods, all pointing to the same conclusion. Something is written on those pages. We just can't see the ink. Tonight, we looked at the candidates for what that writing might say. Particles with different masses, different interactions, different ways of revealing themselves. Each one plausible, each one testable, none confirmed yet. And next time, our next evening together, we'll turn to the other piece of the puzzle, the even larger piece. Not the missing 27%, but the missing 68%. Not dark matter, but something stranger still. Something that doesn't cluster in galaxies, doesn't bend light, doesn't pull things together. Something that seems to be pushing the universe apart. But that's for another evening, another conversation, another time when we sit down together, with the lamp lit and the book open between us. For now, let's just rest here. Let's let the questions settle. The book is still open on the table, but we can leave it there. The shelf is still full of volumes, each one holding a different possibility. And that's all right. We don't need to take one down and declare it the answer. We can let them sit there, side by side, waiting for the experiments to tell us which is correct. The lamp is still steady. Its light hasn't changed. The room is still quiet, still patient. Outside this room, the search continues. Detectors are running. Data is accumulating. Researchers are testing hypotheses with care and precision. But in here, we can rest. We can let the complexity be complex. We can hold the uncertainty without needing to resolve it tonight. Science doesn't rush toward a finish line. It's a process of narrowing uncertainty, of ruling things out, of discovering what the universe is made of, one careful step at a time. And that process doesn't require urgency from us. It doesn't ask us to force conclusions. It asks us to be patient, to stay curious, to trust that the truth will emerge when the evidence is ready to show it. We don't know which book on the shelf holds the right answer yet. Maybe it's WIMPs, maybe it's axions, maybe it's something we haven't thought of, something that will only become clear when a new piece of evidence appears, when a new theoretical framework develops, when someone notices a pattern that's been sitting there all along, but no one quite saw. And that's fine. The universe has been here for 13.8 billion years. It's been holding these secrets for all that time. It can hold them a little longer while we work to understand them. The book will be here when we return. The lamp will still be lit. The questions will still be waiting, patient and open, ready for us to sit with them again. For tonight, that's enough. Rest easy. The search continues, but you don't have to carry it. Just know that it's happening. Know that the experiments are running, that progress is being made, that the field is narrowing step by step. And when there's something new to share, we'll open the book again together. Until then, let the room be still. Let the pages rest. Let the universe keep its mysteries just a little longer. We'll be ready when the answer comes. Here we are again, you and I, back in our quiet room with the lamp burning steadily on the table. The light falls the same way it always does, warm and golden against the pages of our book. The chair beneath you holds your weight with familiar patience. Outside the window, the darkness is complete and gentle, the kind of deep quiet that comes late at night when the world has settled into rest. This is our place. This lamp, this table, this corner of the house where we've been reading together for several nights now. There's comfort in returning here, in finding everything just as we left it. The book still open to where we paused, the blanket within reach if you want it, the sense that we can take all the time we need. We've been reading through this book together for a few nights now. We noticed blank pages scattered through the text, places where something invisible seemed to be written. We confirmed that this invisible writing has weight and presence, that it shapes the way galaxies move and hold together. We looked at a few candidates for what that invisible ink might say, what kind of matter might be filling those blank spaces. Tonight, we turn to a different kind of chapter. Not about what fills the blank pages, but about what the pages themselves are doing. The book we're reading, it turns out, is slowly expanding. The pages are stretching, growing larger in a way that's gentle and persistent. And stranger still, that stretching seems to be getting faster with time. This isn't about dark matter anymore. Dark matter is the invisible scaffolding, the structure that holds galaxies together. What we're turning toward now is something else, something that works in the opposite direction. Where dark matter pulls inward through gravity, this other presence pushes outward, making space itself grow larger. We call it dark energy. And tonight, we're going to look at how we discovered it, what it seems to be doing, and why it remains one of the deepest mysteries we've encountered. Let's set our intention for this chapter before we begin. We're not here to solve this mystery tonight. We're here to sit with it, to understand what we've learned so far and what remains uncertain. This is one of those questions where the discovery itself feels almost impossible, where the evidence pointed towards something so unexpected that it took years for researchers to trust what they were seeing. The universe is stretching. That much we've known for about a century. But the stretching isn't slowing down the way gravity would suggest. It's speeding up. Something is gently, persistently pushing outward, and we don't yet know what it is. That might sound unsettling, but here by the lamp, we can approach it differently. We can treat this as an invitation rather than a void, as a place where our understanding opens rather than closes. Think about what it means to realize that the pages themselves are changing. Not the words we're reading, not the content of the text, but the medium itself. The paper stretching beneath the ink. The chapters growing longer without any new sentences being added. It's a strange realization, the kind that makes you look at the book differently, makes you notice something fundamental that you'd taken for granted. We assume the pages stay the same size. We assume the structure is stable, unchanging, a reliable foundation for whatever story is written there. But what if it isn't? What if the pages have been quietly, patiently expanding all along, and we only just noticed? The universe, as far as current evidence tells us, is vast and ancient and patient. It's been stretching for billions of years. There's no urgency in that stretching, no crisis, just a slow and steady change that we can trace backward and forward through time. We'll take this chapter one page at a time. We'll look at the evidence carefully. We'll acknowledge what we know and what we don't know. And at the end, we'll set the chapter down gently on the table beside the others. Another piece of the larger story we're building together. Let that intention settle for a moment. We're not rushing anywhere. The lamp will keep burning. The chair will keep holding you. We have all the time we need. For now, let's turn the page and step into the first room. Before we can understand what dark energy does, we need to be clear about what cosmic expansion actually is. It's easy to picture it wrong. You might imagine everything flying outward from some central point, like debris scattered across a room. But that's not quite right. Expansion isn't things moving through space. It's space itself stretching. Every part of space in all directions at once, growing gradually larger. Imagine our house, the quiet structure we've been sitting in all season. Now imagine that the rooms themselves are growing, not the furniture moving apart, but the walls gently stretching outward, making each room a little larger with time. A chair in one corner and a lamp in another don't move closer to the walls. The walls move away from them. The distance between any two objects in the room grows, not because anything is traveling, but because the room itself is expanding. What would that feel like if you were standing in such a room? You might not notice it at all at first. The change would be so gradual, so patient, that nothing in your immediate experience would seem different. The chair would still feel solid beneath you. The lamp would still cast the same warm circle of light. But if you measured carefully, if you marked the distance from one wall to another and came back later to measure again, you'd find that the room had grown, not by much, just a little, but measurably, undeniably larger. And if you measured the distance to very distant rooms in the house, rooms far down long hallways, you'd notice something else. The farther away a room was, the faster it seemed to be receding. Not because those distant rooms were moving faster through the house, but because there was more space between you and them, and all of that space was stretching. That's what's happening to the universe. The fabric of space is stretching. Galaxies aren't racing through space away from each other. The space between them is growing. This idea took shape in the early 20th century. Edwin Hubble, working at Mount Wilson Observatory in 1929, measured the light from distant galaxies and noticed something consistent. The farther away a galaxy was, the more its light was shifted toward the red end of the spectrum. This red shift, as we call it, happens when the source of light is moving away from us, or, more accurately, when the space between us and the source is stretching. A Belgian physicist and priest named Georges Lemaitre had already proposed, based on Einstein's equations, that the universe might be expanding. Hubble's observations gave that proposal solid ground to stand on. So by the early 1930s, the picture had changed. The universe wasn't static and eternal. It was dynamic, stretching, evolving. The distant galaxies were drifting farther apart because the space between them was growing. Back here by the lamp, we can rest that foundation on the table. The universe is expanding. That's been part of our understanding for nearly a century. Let it settle there for a moment, a cornerstone of everything that follows. What we didn't know, what wouldn't become clear for decades more, was whether that expansion would continue forever, whether it was slowing down, or whether something else entirely was happening. To answer that question, astronomers needed a way to measure cosmic distances with precision. If you want to know how fast the universe is expanding, you need to know how far away things are and how fast they're moving. The motion part is relatively straightforward. You measure the redshift of a galaxy's light, and that tells you how much the space between you and that galaxy has stretched. But distance is harder. You can't just look at a galaxy and know how far away it is. A dim galaxy might be nearby and faint, or it might be distant and bright. You need some kind of reference, some object whose true brightness you know, so you can compare that to how bright it appears and calculate the distance. We call these objects standard candles. Think of a lamp in a hallway. If you know how bright a lamp actually is, you can judge how far away it is by how dim it looks from where you're standing. A lamp at the end of a long hallway looks fainter than the same lamp held close. This is something we understand intuitively. Brightness and distance have a relationship we can feel. When you see a light in the distance, part of your mind is already calculating how far away it must be based on how bright it appears. The dimmer the light, the farther the hallway must extend. It's a simple principle. But applying it to cosmic distances requires finding objects that are bright enough to be seen across billions of light years, and consistent enough that we can trust their luminosity. In the 1990s, astronomers realized they had a remarkably good standard candle, a specific type of stellar event called a Type 1a supernova. These events happen when a white dwarf star, the dense remnant of a sun-like star, accumulates matter from a companion star. When the white dwarf's mass reaches a critical threshold, about 1.4 times the mass of our Sun, something dramatic happens. The star can no longer support itself, and it undergoes a runaway process that releases an enormous amount of light. This threshold, called the Chandrasekhar limit, is based on fundamental physics. It's the same everywhere in the universe. And because Type 1a supernovae all reach roughly the same mass before they brighten, they all reach roughly the same peak luminosity. That makes them extraordinarily useful. When we see a Type 1a supernova in a distant galaxy, we know roughly how bright it should be at its peak. By measuring how bright it actually appears, we can calculate how far away it is. It's like having a lamp of known brightness that we can place in distant rooms throughout the house, measuring how the light dims with distance, mapping the size and shape of the structure around us. Let that settle for a moment. We have a tool, a way to measure vast distances with reasonable precision. A lamp we can see even when it's very far down the hallway. In the mid-1990s, two groups of astronomers, working independently, began using Type 1a supernovae to map the history of cosmic expansion. One group, called the Supernova Cosmology Project, was led by Saul Perlmutter at Lawrence Berkeley National Laboratory. The other, called the High Z Supernova Search Team, was led by Brian Schmidt, working in Australia, and included Adam Rees among its key members. Both teams had the same goal. They wanted to measure how much the universe's expansion had slowed over cosmic time. The expectation was clear. The universe is filled with matter, and matter pulls things together through gravity. So the expansion should have been faster in the distant past and slower now. The question was, how much slower? That would tell us whether the universe would keep expanding forever, just more and more gradually, or whether gravity would eventually pull everything back together. This wasn't a question with an uncertain answer. It seemed straightforward. We knew the universe was expanding. We knew it contained matter. We knew matter creates gravity. The conclusion felt inevitable. The expansion must be decelerating. The only question was the rate. How much had it slowed? Was it slowing fast enough that the expansion would eventually stop and reverse? Or was it slowing more gently, coasting toward an eternal but ever slower expansion? It was a question you could set out to answer with confidence. The framework was solid. The physics was well understood. The measurements would be difficult, requiring extraordinary precision and care. But the question itself seemed well posed. They spent years developing techniques, finding supernovae, measuring their distances and redshifts, refining their methods. It was painstaking work, careful and methodical, like slowly turning pages in a very long book, checking each one for subtle patterns. What they found, when the data finally came together in 1998, was something neither team expected. The universe's expansion wasn't slowing down. It was speeding up. Both teams arrived at this conclusion independently. They checked their data, looked for errors, tested alternative explanations. The result held. For this discovery, Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics in 2011. Back here by the lamp, we can set that discovery on the table and let it rest for a moment. The careful expectation, the years of painstaking work, and then the data saying something completely different from what the questions had been designed to find. It's one of those findings that feels quiet at first, almost understated, until you sit with it for a while and realize what it means. If the expansion is accelerating, then something we hadn't accounted for must be pushing outward, working against gravity. Let's turn the page and look at that moment more closely. When the data from those distant supernovae came in, both teams noticed the same thing. The supernovae were dimmer than expected, not by much, but consistently across multiple observations, about 20 to 25% dimmer than the models predicted. That meant they were farther away than they should have been. Let's sit with that for a moment. If a lamp in the hallway looks dimmer than expected, it means the hallway is longer than you thought. The light has traveled farther, and so it appears fainter. You stand in the doorway, looking down the corridor. You know how bright that lamp should appear, based on where you think it's placed. But it looks dimmer. Your first thought might be that the lamp itself is different, or that something is blocking the light. But if you check carefully and find that the lamp is exactly what you expected, and nothing is in the way, then you have to consider another possibility. The hallway is longer than you measured. The space between you and the lamp has somehow grown. The lamp hasn't moved, but the distance has increased. That's what the supernova data was saying. In cosmic terms, if the distant supernovae were farther away than expected, it meant the universe had expanded more than it should have over the time since those supernovae occurred. The stretching had been faster than the models predicted, and if the stretching had been faster, that meant the expansion wasn't slowing down under gravity's pull. It was speeding up. Both teams ran systematic checks. They looked for dust that might be dimming the light. They examined whether the supernovae themselves might be intrinsically fainter in the distant past. They tested whether their distance measurements might be off. They compared their calibrations, their methods, their assumptions. The conclusion held. The supernovae really were farther away than expected. The expansion really was accelerating. And here's what made the result credible. Both teams found the same thing, independently, working with different approaches, different observing strategies, different analysis methods. They weren't collaborating. They didn't know what the other group was finding until the results were nearly complete. Two separate groups asking the same question, using the same kind of evidence, arriving at the same unexpected answer. That's what science looks for. Not just one surprising result, but independent confirmation. It was one of those moments in science where the data says something clear and surprising, and you have to decide whether to trust it. Both teams trusted it. And the announcement in 1998 changed the entire chapter. Let's imagine tossing a ball gently upward. Gravity pulls the ball downward, slowing its ascent. You expect it to rise quickly at first, then more slowly, then stop and fall back down. The ball's speed decreases over time because gravity is working against its motion. That's what we expected for the universe's expansion. Matter creates gravity, and gravity pulls things together, so the expansion should slow over time. The question was whether it would slow enough to eventually reverse, or whether it would keep going forever, just more and more gradually. But what the supernova data showed was the equivalent of tossing a ball upward and watching it rise faster and faster instead of slower. The speed increasing rather than decreasing. The sign was wrong. Something was pushing outward, gently and persistently, working against gravity's inward pull. For the scientific community, this was a moment of quiet recalibration. Not panic, not alarm, but a willingness to let the evidence reshape the story. The framework that had seemed so solid, the expectation of deceleration, had to be set aside. This is what science does at its best. It remains open to being surprised. It builds careful expectations based on the best available understanding, and then it's willing to revise those expectations when the data points elsewhere. Back here by the lamp, we can acknowledge that this was deeply unexpected. The equations didn't predict it, the models didn't require it, and yet the evidence pointed clearly toward it. The discovery from the two supernova teams was remarkable, but it was also so unexpected that researchers needed independent confirmation. That confirmation came from multiple directions over the following years. One line of evidence came from studying the cosmic microwave background, the faint afterglow of the hot, dense state the universe was in about 13 billion years ago. This light carries patterns, subtle variations in temperature that encode information about the universe's composition and geometry. Two space missions, WMAP launched in 2001 and Planck launched in 2009, mapped these patterns with extraordinary precision. What they found was that the universe is spatially flat, not curved inward like the surface of a sphere, not curved outward like a saddle, but flat, like the pages of a book laid open on the table. Let that observation rest for a moment. Flatness. It sounds simple, but it has implications. That flatness has a specific meaning. If you add up all the energy in the universe, the total should equal a specific critical density. WMAP and Planck measurements showed that ordinary matter and dark matter together make up only about 31 to 32% of that total. The rest, about 68 to 69%, had to be something else. Something that didn't behave like matter. Something consistent with the accelerating expansion the supernova teams had found. Another line of evidence came from studying patterns in how galaxies are distributed across space. In the early universe, sound waves traveled through the hot plasma before atoms formed. When atoms finally did form, those sound waves froze in place, creating a characteristic scale, a preferred distance of about 490 million light-years, where galaxies would later tend to cluster. We call these patterns baryon acoustic oscillations. They act as a kind of standard ruler, a known distance we can use to map cosmic expansion at different times. Large galaxy surveys measured these patterns and found the same thing the supernovae had shown. The expansion was accelerating. So by the mid-2000s, we had three independent methods. Three different ways of looking at the universe. Each one could have disagreed with the others. Each one could have pointed in a different direction, forcing us to choose which to trust, or to acknowledge that we didn't understand something fundamental. But they didn't disagree. They converged. Supernovae said the expansion is accelerating. The cosmic microwave background said there's energy we haven't accounted for. Galaxy clustering said the same thing from yet another angle. Three lines of evidence, all pointing toward the same conclusion. The expansion is speeding up. Something we call dark energy, for lack of a better name. makes up about 2/3 of the universe's total energy content. The data converged. The story had to change. Back here by the lamp, we can set those 3 lines of evidence on the table, side by side. Supernovae, the cosmic microwave background, galaxy clustering, all of them saying the same thing, each one strengthening the others. Let's rest here for a moment before we ask the next question. What is this dark energy? What could possibly cause the universe to stretch faster over time? To understand one possible answer, we need to go back about a century, to a time before we knew the universe was expanding at all. Albert Einstein, working through his new theory of gravity in 1915 and 1916, found something troubling. His equations suggested that the universe couldn't simply sit still. Gravity would pull everything together, collapsing the whole structure inward. But astronomers at the time saw a cosmos that seemed stable, eternal, unchanging. So in 1917, Einstein added a term to his equations. He called it the cosmological constant, usually written as the Greek letter lambda. It represented a kind of gentle outward pressure built into space itself, a way to balance gravity's inward pull and keep the universe steady. It seemed like a reasonable adjustment, a small mathematical note to make the theory match what was observed. But within a few years, as we discussed earlier, evidence began to suggest the universe wasn't static at all. Lemaitre proposed expansion based on the equations. Hubble observed it in the motion of distant galaxies. If the universe was expanding anyway, there was no need for that extra term. Einstein, according to accounts from physicist George Gamow, later referred to the cosmological constant as his biggest blunder. So lambda was set aside, left on a shelf like a book we thought we'd finished with. For decades, it seemed like a discarded idea, a mistake, a mathematical artifact that didn't correspond to anything real. But after 1998, when the evidence for accelerating expansion became clear, researchers realized they might need to take that book off the shelf again. The simplest explanation for dark energy is that Einstein's cosmological constant is real, not a mistake, but a fundamental property of space itself. In this view, dark energy isn't a substance or a field that moves or changes. It's woven into the structure of space, like energy embedded in the walls of our house. Every cubic meter of empty space carries a tiny amount of this energy. And as the universe expands, creating more space, there's more total energy pushing outward. More wall means more wall energy. More space means more dark energy. That's why the acceleration can continue, even grow stronger over time. Think about what that means. The rooms in our house are growing. As they grow, the walls stretch. And as the walls stretch, they carry more of this energy with them. The energy isn't added from somewhere else. It's not flowing in from outside. It's intrinsic to the walls themselves. More wall, more energy. It's an elegant idea, simple in its mathematics, consistent with the observations, and remarkably minimal in its assumptions. Let that image settle. The walls of space carrying their own gentle outward pressure, not violently, not dramatically, but patiently and persistently, making the rooms grow. But it comes with a deep puzzle. When physicists try to calculate what the cosmological constant should be, using quantum field theory, they run into a problem. The calculation gives a number, but that number is wrong. not a little bit wrong, not off by a factor of 2 or 10 or even a million. The theoretical prediction is larger than the observed value by a factor of about 10 to the power of 120. That's a 1, followed by 120 zeros. It's one of the largest discrepancies between theory and observation in all of physics. Imagine it this way. The mathematics says the walls should be vibrating with enormous energy, enough to make the entire house unrecognizable, unstable, completely unlike what we observe. But when we measure the walls, we find them almost perfectly still. Just the tiniest, gentlest pressure, barely there at all. We don't know why this is. We don't know if there's some mechanism that cancels out most of the vacuum energy, leaving only the tiny amount we observe. We don't know if our theoretical framework is missing something fundamental. We don't know if the question itself is being asked correctly. It's a puzzle that remains open. We can acknowledge it without forcing a resolution. We can set it on the shelf as a question we haven't answered yet, a place where the chapter still has blank pages. What we can say is this: the observed value of the cosmological constant, whatever its origin, is very small but not zero. And that small value is enough to make the universe's expansion accelerate. Let's step back and look at the whole picture, the model that's emerged from all this evidence. We call it lambda CDM. Lambda for the cosmological constant, representing dark energy. CDM for cold dark matter, the invisible scaffolding we discussed in previous chapters. Based on current evidence, the universe's total energy content divides roughly like this: about 68% dark energy, about 27% dark matter, and about 5% ordinary matter. That ordinary matter includes everything we can see and touch: stars, planets, gas clouds, galaxies. You and I sitting here by the lamp. It's a small fraction of the total. Dark matter is the structure that holds galaxies together, the invisible weight that shapes how matter clumps and clusters. Dark energy is the gentle outward push that makes space stretch faster over time. Together, they make up about 95% of everything. The missing 95% that gives this season its name. This model, lambda CDM, fits the data we have remarkably well. The observations from supernovae, from the cosmic microwave background, from galaxy surveys, from gravitational lensing, all of it fits together into a coherent picture. Does that mean the model is final, complete, the last word? No, science doesn't work that way. Models are tools, maps, ways of organizing what we know. They're useful when they fit the evidence and make accurate predictions. And lambda CDM does both of those things. But we also have to be honest about what we don't understand. We don't know why the cosmological constant has the value it does. We don't know if it's truly constant, or if it might change slowly over cosmic time in ways we haven't detected yet. We don't know what dark matter is made of. Think about what it means to work with a model you know is incomplete. It's not a failure. It's the nature of understanding itself. We build the best framework we can with the evidence available. We use it to make predictions, to guide observations, to organize our thinking, and we remain ready to revise it when new evidence arrives. That's the position we're in now. Lambda CDM works. It fits what we see. It's the best map we have. But we know there are territories on that map marked with uncertainty. places where the details remain unclear. The model works. It organizes the evidence. It makes predictions that we can test. But there are still blank pages, still questions resting in the margins. Back here by the lamp, we can accept that. We can hold both things at once, a model that fits the data well, and an acknowledgement of what remains uncertain. Let's turn to one more puzzle before we close this chapter. There's a number at the heart of cosmic expansion, a measure of how fast the universe is stretching right now. We call it the Hubble constant, named after Edwin Hubble, and we write it as H0. It tells us how much faster distant galaxies are receding for every additional megaparsec of distance between us and them. You'd think measuring this number would be straightforward. After all, we've been studying cosmic expansion for nearly a century. We have multiple methods, sophisticated instruments, careful observations. But here's the puzzle. We have two primary ways of measuring H0, and they give us two different answers. One method looks at the early universe. We study the cosmic microwave background, that faint afterglow from when the universe was about 380,000 years old. From the patterns in that ancient light, using our best models of how the universe evolves, we can calculate what the expansion rate should be today. It's like measuring the rooms in our house by looking at the original blueprints, the plans from when the structure was first built. You can see the dimensions as they were drawn. You understand the construction principles, how the house was meant to be built. And from those blueprints, you calculate forward. If the house was built according to plan, if it's aged and settled in predictable ways, then the room should be this size now. The other method looks at the nearby universe. We measure distances to objects like Cepheid variable stars and Type 1a supernovae, building a distance ladder step by step, and we calculate the expansion rate directly from the motion we observe. It's like measuring the rooms with a tape, moving from one reference point to the next, determining the size of the house as it exists right now. You start with nearby objects, whose distances you can measure reliably. You use those to calibrate the next rung of the ladder. Step by step, you extend your measurements farther and farther until you can map the expansion directly. Both approaches are careful. Both are based on solid physics. Both have been refined over years of work by multiple independent teams, and you'd expect them to agree. The blueprint should match the tape measurements. The calculation from the early universe should give you the same answer as the direct observation of the nearby universe. But they don't agree. And that disagreement creates a quiet unease, a sense that something in our understanding might need adjustment. The early universe method, using data from the Planck satellite and our best cosmological models, gives us a Hubble constant of about 67.4 kilometers per second per megaparsec. The nearby universe method, using observations of Cepheid stars and supernovae, calibrated with data from the Hubble Space Telescope, and more recently from the James Webb Space Telescope, gives us a value closer to 73 kilometers per second per megaparsec. That's a difference of about 8%. It might not sound like much, but in cosmology, where measurements are made with extraordinary precision, it's significant. The statistical significance of this disagreement is greater than 5 sigma. In the language of physics, that means the probability of this being just a random fluctuation, just bad luck in how the measurements happen to come out, is extraordinarily small, less than 1 in a few million. This isn't a marginal difference that might go away with more careful work. This is a substantial disagreement that's been confirmed and sharpened over years of increasingly precise observations. The James Webb Space Telescope, with its remarkable sensitivity, has confirmed the accuracy of the nearby universe measurements. The Cepheid distances, the calibration of the distance ladder, those appear to be solid. The systematic errors that researchers worried about, the subtle effects that could throw off the measurements, those have been checked and rechecked. So the tension isn't going away. If anything, it's sharpening. The more carefully we measure, the clearer the disagreement becomes. Back here by the lamp, we can acknowledge that this is genuinely puzzling. Two careful methods, both based on sound principles, both refined by skilled researchers, and yet they give different answers. We call this the Hubble tension. It's one of those places where the chapter is still being written. If the tension is real, if it's not just some subtle error we haven't found yet, it could be pointing towards something new. One possibility is that dark energy behaves differently than we think. Perhaps it's not truly constant. Perhaps it has changed over cosmic time in ways our current models don't account for. That would affect how we calculate the expansion rate from early universe data. The blueprints would need revision. The assumptions we make about how the house ages, how the rooms grow over time, those might need adjustment. Or perhaps there's something about the early universe itself that we've misunderstood. Some component or interaction that affects the cosmic microwave background but doesn't show up in nearby measurements. Or maybe our understanding of cosmic distances needs refinement. These are difficult observations, pushing the limits of what our instruments can do. Even small systematic effects can shift the results. Researchers are working on this from multiple angles. New observations, independent checks, alternative methods. The goal is to either resolve the tension or confirm that it's telling us something genuinely new about how the universe works. And here's what this tension means for the larger story we've been building this season. The missing 95% keeps surprising us. We thought we understood dark matter well enough to map its distribution. We're still looking for what it's made of. We thought we understood dark energy as a simple cosmological constant. Now we have a tension that might be suggesting it's more complicated. Even our best model, Lambda CDM, the framework that fits so much of the data so well, has this unresolved thread running through it. This place where the measurements don't quite agree, where the story might need another revision. For now, we can leave this question resting on the shelf. It's an invitation, not a conclusion. A place where the evidence is pointing towards something we don't fully understand yet. We don't need to force an answer tonight. We can acknowledge the tension, note what it might mean, and keep reading. Back here by the lamp, we can rest with that uncertainty. It's one more blank page in the book, one more place where the chapter opens rather than closes. And that's all right. That's how understanding grows. Not by filling every page at once, but by noticing where the blank spaces are and being patient with them. Let's gather the pages we've turned tonight and see how they fit together. We began with the discovery that the universe is expanding. That realization, which took shape nearly a century ago, changed our picture of the cosmos from something static and eternal to something dynamic and evolving. We saw how astronomers developed ways to measure that expansion with precision, using Type 1a supernovae as standard candles, lamps of known brightness placed in distant rooms throughout the cosmic structure. We looked at the work of two independent teams, Saul Perlmutter's Supernova Cosmology Project and Brian Schmidt and Adam Rees's High Z team, who both discovered in 1998 that the expansion isn't slowing down, but speeding up. Something is pushing outward, gently and persistently, against the inward pull of gravity. We saw how that discovery was confirmed through multiple independent methods. The cosmic microwave background showed us that the universe is flat, and that matter alone can't account for its total energy content. Patterns in galaxy clustering provided another line of evidence pointing toward the same conclusion. We explored what dark energy might be. The simplest possibility is Einstein's cosmological constant, resurrected after decades on the shelf. A property of space itself, energy woven into the walls of the universe. More space, meaning more energy. We acknowledged the vacuum energy problem, that vast mismatch between theoretical prediction and observed value. A puzzle that remains open, a question we haven't resolved. And we looked at the Hubble tension, the disagreement between two careful methods for measuring the current expansion rate. A place where the evidence might be pointing towards something new, something we don't yet understand about how the universe evolves. These aren't neat answers. They're more like open doorways, thresholds where one chapter ends and another begins. Let's step back further and see where we've been across these 4 nights. We began this season by noticing the blank pages scattered through our book. Pages where something invisible seemed to be written. We called them the missing 95%. The vast majority of the universe's content that we can't see directly. In the first episode, we asked whether those blank pages were really there, or whether we might be misreading the text. We looked at the evidence for dark matter and found it remarkably strong, woven through multiple observations from galaxy rotation curves to gravitational lensing to the cosmic microwave background. In the second episode, we confirmed that something invisible is written on those pages. We saw how dark matter shapes the formation of cosmic structure, how it acts as scaffolding around which galaxies and clusters can form and grow. In the third episode, we looked at candidates for what that invisible ink might say. What is dark matter made of? We examined several possibilities, from WIMPs to axions to primordial black holes, and found that the question remains open. Tonight, we discovered that the blank pages aren't just blank. They're expanding. The book itself is growing, the pages stretching gently outward. And that stretching is getting faster with time. The missing 95% isn't passive or inert. It's active. Dark matter pulls things together, shaping structure. Dark energy pushes things apart, making space itself grow. Together, they define how the universe evolves over cosmic time, how galaxies form and cluster, how the expansion proceeds, how the future might unfold. In the chapters ahead, we'll continue turning these pages. We'll look at how researchers are trying to map dark energy more precisely, to test whether it's truly constant or whether it might be something more dynamic. We'll consider what the long-term future might hold for a universe that's accelerating outward. But that's for another night. For now, we've turned enough pages. Let's set this chapter down gently on the table beside the others. The universe is stretching. That's what tonight's reading tells us. Not violently, not urgently, but with a patient and persistent pressure that's been building for billions of years. Something we call dark energy, whether it's the cosmological constant or something more subtle, is gently pushing outward, working against gravity, making the space between distant galaxies grow a little faster with each passing moment. We don't fully understand it. We don't know why it has the value it does, or whether it will remain constant forever, or what it means for the long-term future of everything. But we know it's there. The evidence is clear and consistent and convergent. Multiple lines of observation, independent methods, all pointing toward the same conclusion. That's enough for tonight. We don't need to resolve every question. We don't need to turn every blank page into filled text. We can leave some questions resting in the margins, acknowledging what we know and what we don't know, holding both with the same patient attention we've brought to everything else in this season. The lamp is still burning. The chair is still steady beneath us. The window shows the same quiet darkness it always has. And the book is still here, waiting for us to turn the next page, whenever we choose. Rest well. Back here by the lamp, in this quiet room where we've been sitting together these past few evenings, the light is the same as it was, soft, steady, the kind of light that doesn't strain the eyes, that lets you read for hours without noticing the time passing. The chair is familiar now, the weight of it, the way it holds you without demanding attention. This is our 5th evening with the missing 95%. 5 times we've returned to this room, to this lamp, to these pages spread out before us. There's a rhythm to it now, a pattern of return. We've been building something slowly, carefully, like arranging books on a shelf in the order they were meant to be read, each evening adding another volume, each conversation settling into the space the previous ones created. We noticed the blank pages in the universe's ledger. We confirmed something is written there. We looked at the candidates for what dark matter might be. Last time, we discovered that the pages themselves are expanding, that space is stretching gently across distances we can barely hold in mind. And we met the simplest explanation for that expansion: lambda, the cosmological constant, an idea with a century of history behind it, a placeholder name for the gentle push that seems to be woven into space itself, the same everywhere, the same strength through all of cosmic time. We left it there. Lambda on the shelf, a constant push. But tonight, we're going to open that question again, because there's something we didn't ask last time. We accepted that there's a push. We accepted that it seems steady. But we didn't ask whether it actually is steady, whether the strength of this push has always been the same, or whether it might be changing. Not changing quickly, not changing in ways we'd notice in a human lifetime, or in 1,000 human lifetimes, but changing slowly, patiently, across billions of years, in ways that telescopes might be able to measure, if they're careful enough and patient enough. Back here by the lamp, that might sound like a small detail, a footnote, something that wouldn't change the main story. But it's not. If the push is truly constant, if lambda is exactly what the equations describe, then it's a fundamental property of space itself, woven into the fabric of the universe at the deepest level. Fixed, structural, part of the walls, But if the push is changing, even slightly, then it's something else. Something dynamic. Something that has a history, that evolves, that might surprise us. The pages we thought were settled might be shifting under gentle pressure we hadn't noticed. Not the words changing, not the ink lifting off the paper, but the paper itself, the medium, the substance, responding to something we haven't fully understood, adjusting its texture, its weight, its readiness to hold what's written on it. What does it feel like to realize that? To think the ground beneath the text might be moving, just barely, in ways you'd need very careful instruments to detect. Not unsettling exactly, more like curious. Like noticing the floorboards in an old house settle slightly with the seasons. The house is still solid, still safe, but it's responding to forces you hadn't been paying attention to. We can sit with that possibility for a moment before we ask how to test it. Here in the quiet, here where there's no hurry. This isn't just about refining a number. It's about understanding what kind of universe we're living in. If the push is constant, then we can predict the future with some confidence. The expansion will keep accelerating, gently, forever. Galaxies will drift apart. The universe will grow quieter, emptier, cooler, over timescales we can barely name. The long rest. But if the push is changing, if it's growing stronger or weaker, or following some pattern we haven't seen yet, then the long-term story might be different. The ending might surprise us. And so, quietly, patiently, researchers have been asking, how would we even test this? How would we measure whether something as vast and subtle as dark energy is changing across cosmic time? That's what we're here to explore tonight. Not the answer. The answer isn't settled yet. But the question itself, the tools, what we're beginning to see, what the measurements are whispering. Here in our quiet room, we can turn the page gently and see what's written there. Let me offer you a way to hold this. Imagine you're standing in a hallway and you press your hand against the wall. You can feel the wall pressing back. That's positive pressure. The wall resists. It pushes against your hand with the same strength that your hand pushes against it. Now imagine the opposite. Not the absence of pressure, but pressure in reverse. Imagine the wall is somehow pulling your hand toward it, gently but persistently, as if the space between the wall and your hand wants to shrink. As if the wall has a kind of attraction, a draw rather than a push. That would be negative pressure. It would feel strange, unfamiliar. Your instincts wouldn't know what to make of it. You'd press forward, expecting resistance, and instead feel a kind of yielding, a gentle invitation inward. Not forceful, not grabbing, just a patient pull, like the way a soft blanket settles around your shoulders. This is the idea behind something called the equation of state parameter, which researchers label with the letter W. It's a way of describing how pressure and energy density relate to each other. A kind of ratio, a comparison. For ordinary matter, the matter we're made of, the matter in stars and planets, whiz positive. Matter pushes outward when you compress it. But for dark energy, for lambda, W equals -1. That's what a cosmological constant looks like. Negative pressure. A steady pull that doesn't change with time, doesn't dilute as space expands. just remains the same, everywhere, always. And here's the question researchers are asking. What if W isn't exactly -1? What if it's -1.1 or -0.9? What if it's changing over time? If W is exactly -1, then dark energy is lambda, a constant, a fixed property of space-time itself. But if W is anything else, even slightly different, then dark energy is something more dynamic, something that can evolve, something that has a shape we haven't fully traced yet. Back here in our quiet room, we can think of it this way. Lambda is like the walls themselves, fixed, structural, part of the house. You can't adjust them, they simply are. But if W is not -1, then dark energy is more like a presence in the room that can change. Not wildly, not quickly, but gradually, in response to conditions we don't yet understand. And if W is changing over cosmic time, if it was one value 10 billion years ago and a different value today, that tells us even more. It tells us the push isn't just variable in principle. It's actually evolving right now in ways we might be able to trace. We'll explore what that might mean later tonight. For now, let's stay with the question of how you'd measure it. Researchers have developed a way to parameterize this, to capture it in a form that telescopes can test. They use two numbers. The first, W0, describes the value of W today, right now, in our present epoch. The second, WA, describes how W has been changing over cosmic time. Think of it this way. W0 tells you how hard the walls are pressing right now, in this moment, in the room where we're sitting. WA tells you whether that pressure has been changing, whether it was stronger or weaker in the past, and by how much. If W sub A is 0, then W has been constant, no change, lambda. But if W sub A is not 0, then W has been evolving, and the size of W sub A tells you how fast. Two numbers. That's what the whole question reduces to. A snapshot and a trend. Where we are and how we got here. Back here by the lamp, we can hold those two numbers like coordinates on a map. W0 describes the walls right now, their texture, their solidity. WA describes their history, whether they've always been this way, or whether they've been settling, adjusting, responding to the weight they carry. And the deviations researchers are looking for are small, a few percent over billions of years, subtle shifts that require extraordinary precision to detect. So how would you measure whether W is changing? You'd need two things. First, you'd need very accurate measurements of cosmic distances, how far away galaxies are, and how fast they're moving away from us. And second, you'd need those measurements at different points in cosmic history, so you can compare the strength of the push in the early universe to the strength of the push today. Think of it like reading a book where the margins get wider as you turn the pages. If you only look at one page, you might not notice. But if you compare page 10 to page 100 to page 500, you can see the pattern emerging. The deviations might be only a few percent, like noticing the margins have widened by a fraction of a millimeter across 500 pages. You'd need to measure carefully. You'd need to be sure the change isn't just a printing variation, or a trick of the light, or the way you're holding the book. Researchers do this by measuring objects called Type 1a supernovae, stars reaching the end of their lives in a particular way that produces a known brightness. If you measure how dim they look from Earth, you can calculate how far away they are. And because light takes time to travel, looking at distant supernovae means looking back in time. By measuring supernovae at different distances, different moments in cosmic history, researchers can trace how the expansion rate has changed over billions of years. And from that, they can infer whether the push is constant or evolving. But there's another method, one that doesn't rely on supernovae. It uses something called baryon-acoustic oscillations. Back in the very early universe, when everything was hot and dense, sound waves rippled through the plasma. These ripples left a subtle pattern in the way matter is distributed today. A characteristic scale, a particular distance, like a faint echo preserved in the arrangement of galaxies. Researchers can measure this pattern by mapping millions of galaxies and looking at how they cluster. The scale of the clustering acts like a ruler, a standard length, which lets them measure cosmic distances in a different way from supernovae. And one telescope in particular has been doing this work. Quietly, patiently, night after night. A telescope in the Arizona desert, collecting light from millions of galaxies, building a map of the universe's expansion history with extraordinary care. Let's step into that room. The Dark Energy Spectroscopic Instrument, DESI, sits at the Kitt Peak National Observatory in Arizona, perched on a mountain under dark skies. It's attached to a telescope that was built decades ago, but the instrument itself is new, designed specifically for one purpose: to map the three-dimensional positions of millions of galaxies across cosmic time. It does this by measuring redshift, the stretching of light caused by cosmic expansion. The more stretched the light, the farther away the galaxy, and the further back in time we're seeing it. DESI can observe 5,000 galaxies at once. It has 5,000 tiny robotic positioners, each one moving independently, precisely, to point a fiber optic cable at a different galaxy. Each night, it collects light from thousands of galaxies. Each month, hundreds of thousands. Over the course of its survey, DESI is measuring more than 40 million galaxies and quasars, creating the most detailed three-dimensional map of the universe ever made. This is work that involves over 900 researchers from 70 institutions across the globe, astrophysicists, engineers, data scientists, people who design instruments, people who observe with them, people who analyze what the observations reveal. A collaboration that spans continents, languages, time zones, brought together by a single question. Back here by the lamp, we can think of it as turning millions of pages at once, each one a snapshot of the universe at a different moment, and arranging them in order so we can see how the story unfolds, how the margins change, how the spacing shifts. That's the kind of patience this work requires. Not the patience of waiting for something to happen, but the patience of careful measurement, repeated observation, methodical checking and cross-checking until you're sure what you're seeing is real. In April 2024, DESI released its first set of results. These came from the survey's first year, about 6 million galaxies and quasars, measured with care, their positions mapped, their distances calculated. And those results contained something unexpected. Not a conclusion, not a proof, but a hint, a whisper. The researchers had set out to measure whether lambda was exact, to confirm what most cosmologists expected, that dark energy is a cosmological constant, unchanging, fundamental. The goal was precision, refinement, narrowing the uncertainties. Instead, the data whispered something different. The measurements suggested that W might not be constant, that it might have been slightly different in the early universe than it is today, that the push might have a history. This was the kind of surprise that comes from careful, methodical work. Not dramatic, not sudden, just a detail in the data that didn't quite match expectations. A pattern that appeared in multiple ways of analyzing the results, quietly insistent. Back here by the lamp, we can feel the weight of that moment. The researchers checking their methods, running the analysis again, considering whether this could be a statistical fluctuation, a systematic error, or something real. The statistical significance was about 2.5 to 3 sigma, which in scientific terms means interesting, but not definitive. Researchers generally wait for 5 sigma before calling something a discovery, a standard that requires extraordinary evidence. So what Desi found was more like a detail noticed in the margin, something that might be meaningful or might be a trick of the light. But it was a whisper that appeared in multiple ways of analyzing the data. Different methods, different assumptions, and in each case, the hint pointed in the same direction. Here in our quiet room, we can set that page on the shelf. The 2024 result, the first hint, and we can turn to what came next. In March 2025, Desi released its second dataset. This one came from 3 years of observations, nearly 15 million redshifts, more than double the data from the first release. A larger volume of space, a wider range of cosmic time, more galaxies, more quasars, more careful measurements extending further back into the universe's history. More pages in the book, more carefully arranged. Think about what that means. 15 million individual measurements, each one requiring the telescope to point precisely, the fiber optic cable to capture light that's been traveling for billions of years, the spectrograph to analyze that light and measure how much it's been stretched. 15 million data points, each one a thread in a vast tapestry, and the hint strengthened. The evidence for evolving dark energy increased. Depending on how the data were analyzed, the statistical significance rose to between 2.8 and 4.2 sigma. Still not 5 sigma. Still not definitive, but closer, more consistent, harder to dismiss as statistical noise. One detail matters here. The DESI collaboration used what's called a blinded analysis. The researchers didn't see the actual results until after they'd finalized their methodology, their ways of measuring, their ways of testing for systematic errors. This is a discipline borrowed from particle physics, a way of ensuring that human expectations don't subtly shape the results. You decide how you'll analyze the data before you look at what the data say. You commit to your methods while the answer is still hidden. Only then do you remove the blindfold. It requires a particular kind of trust. Trust in the process. Trust in your colleagues. Trust that the methodology is sound enough to stand on its own, without needing adjustment based on what the results turn out to be. When they unblinded the data and saw what it showed, the evidence for evolution was still there. The measurements pointed, quietly but persistently, in the same direction. The collaboration noted, carefully, that the standard cosmological model might need modification. Not a declaration, not a claim of discovery, but an acknowledgement that something interesting is appearing in the data, and it's worth taking seriously. This is science at its most careful, not rushing to conclusions, not ignoring signals, but noting them honestly and continuing to watch, letting the evidence accumulate, letting the picture develop at the pace the universe allows. Back here by the lamp, we can pause and feel the weight of that. As of early 2026, Desi is still observing, still collecting light, still turning pages. The survey continues. So what is the hint saying? The data suggests that W was more negative in the past than it is today. In other words, the push may have been stronger billions of years ago, and it's been gradually weakening over cosmic time. Not quickly, not dramatically, but measurably, if the hint holds up. Another way to say it, the push may be getting gentler over time. Here in our quiet room, we can sit with that possibility for a moment. Not with alarm, not with excitement, just with curiosity. The universe might be settling into a different kind of acceleration than we thought. The expansion might have a more complex history than a simple constant push. What would it mean if that's true? We'll explore that question in a few minutes. For now, we can just notice it, hold it lightly, let it rest on the shelf alongside the other possibilities. This is still tentative. Many signals at 3 or 4 sigma have appeared in the history of cosmology and then faded when more data arrived. It's possible this one will too. The universe might be showing us a pattern that isn't really there, a detail in the margin that turns out to be a smudge. But it's also possible the pattern is real, that dark energy is not lambda, that the push has a history, a shape, an arc we're only now beginning to trace. The survey is planned to run for 5 years total. More data will come, more measurements, more careful analysis, and with each new release the picture will sharpen, the uncertainties will narrow, the whisper will either strengthen into a clear voice or fade into silence. Here in our quiet room, we don't need to decide tonight. We can let both possibilities rest on the shelf side by side. The instrument is watching. The question remains open. And that's enough for now. If W is changing, if dark energy is evolving over time, then it's not the cosmological constant. It's something else. The most common theoretical framework for this is called quintessence. The word itself is old, reaching back to Aristotle, who proposed that beyond the 4 elements, earth, water, air, fire, there was a 5th element, the quintessence that filled the heavens, the ether, the substance of the celestial realm. The ancients gave it a name because they sensed there must be something more, something beyond what they could touch or see or hold, a presence that filled the spaces between the stars, that held the cosmos together, that explained why the heavens moved the way they did. We're still learning whether they were onto something. Not the literal 5th element. That idea dissolved centuries ago. But the intuition that there might be a substance, a field, a presence filling space that we don't yet understand. Modern quintessence isn't the same idea, but it borrows the name. It refers to a family of theories based on the concept of a scalar field, a kind of energy that fills space. But unlike lambda, it can vary in strength. It can change over time or from place to place. Think of it this way. Lambda is like the walls of the house, fixed, structural, always the same. But a scalar field, quintessence, is more like temperature. It can be warmer in one room, cooler in another. It can shift as conditions change. It has a dynamic presence. There are many possible versions of quintessence, depending on how the field behaves. Some models, called thawing models, suggest the field was essentially frozen in the early universe and has only recently started to evolve. Others predict slow, steady changes over cosmic time. Still others predict oscillations or cycles. And here's the thing. None of these models were written down to explain Desi's hint. They were proposed decades ago as ways of thinking about what dark energy could be if it weren't lambda. Desi's data, the whisper it's hearing, is consistent with some of the thawing models. Not proof, but alignment. A match between theory and observation that wasn't forced. Here by the lamp, quintessence is a possibility resting in the margin. Not the main text yet. Not proven. Just a candidate, written carefully, waiting to see if the evidence grows stronger. If W has been changing, that means the history of cosmic expansion is slightly different from what we thought, and it means the future might unfold in different ways. There are three broad possibilities, 3 pages we might turn to in the long run. First, if W is truly constant, if lambda is the answer, then the expansion will keep accelerating, gently, forever. Galaxies will drift apart. The universe will grow quieter, emptier, cooler, over timescales we can barely name. Imagine it. The stars burning out, one by one, over trillions of years. The galaxies fading, the distances between them growing so vast that light can no longer cross them. The universe becoming a collection of isolated islands, each one drifting alone in an ocean of expanding space. The long rest, the gradual evening, a settling into silence that has no end. Second, if W is weakening, if the push is getting gentler over time, then the acceleration might slow. Not soon, not in any time frame that would affect stars or galaxies or the stability of planetary systems, but far in the future, measured in many tens of billions of years, the acceleration might ease, and in principle, it could even reverse. The universe might eventually stop expanding and begin to draw inward again. Not collapse, not catastrophe, just a different kind of settling. Third, if W is strengthening, if the push is getting more intense, then the acceleration will intensify as well. This seems less likely based on current hints, and if it were happening quickly, it would lead to scenarios researchers sometimes call phantom energy. But we don't need to dwell on those. They're speculative, and the data aren't pointing that direction. Back here by the lamp, we can think of it as adjusting the angle of a bookshelf just slightly. If the shelf is perfectly level, books sit flat. But if it's tilted, even slightly, the books slide. Not fast, but over time the change becomes visible. The arrangement shifts. None of these possibilities require urgency. The timescales are so vast, they dwarf everything we know. Billions of years, trillions of years. Numbers so large they lose meaning, become abstract, settle into the realm of ideas rather than experiences. If W is changing, it's changing so slowly that nothing in our experience would feel different. The Earth would continue its orbit. The sun would continue to shine. The galaxies we can see would continue to be visible for timescales far longer than humanity has existed. What's changing, if anything, is our understanding. The room we're standing in is the same, but we're noticing details we hadn't seen before. The way light falls on the walls, the way the floor slopes just slightly, the way the pages turn. Let me add a few margin notes here. Ideas written in pencil, not ink. If dark energy is evolving, quintessence is one possibility, but there are others. Some researchers are exploring models where dark energy isn't a field at all, but a sign that general relativity, Einstein's theory of gravity, needs revision on cosmic scales. Modified gravity. The idea that the equations work well for planets and stars, but might need adjustment when applied to the entire universe. Others are considering coupled dark energy, models where dark energy and dark matter aren't entirely separate, but interact in subtle ways. Or early dark energy, the idea that there was a brief episode of extra push in the early universe that affected its development. These are speculative frameworks. Most of them will probably turn out to be wrong, but they're part of the process. You propose ideas, you test them against data, you see which ones survive and which ones fade. Margin notes, written in pencil, ready to be erased or promoted as the evidence develops. Here in our quiet room, we can leave these notes in the margins where they belong. Not the main text, just possibilities held lightly, waiting to see if the evidence strengthens or dissolves. DESI isn't the only telescope watching. In July 2023, the European Space Agency launched a satellite called Euclid, designed to map the shapes and positions of billions of galaxies from space, above the distortions of Earth's atmosphere. Euclid measures baryon acoustic oscillations, like DESI, but it also measures something called weak gravitational lensing, the subtle way dark matter and dark energy bend light as it travels across cosmic distances. Here's how that works. When light from a distant galaxy travels toward us, it passes through regions of space that contain dark matter. The dark matter's gravity bends the light just slightly, distorting the galaxy's shape. If you measure thousands or millions of galaxies, you can see the statistical pattern of these distortions. And from that pattern, you can infer how much dark matter is present, how it's distributed, and how dark energy is affecting the expansion. Euclid isn't just counting galaxies. It's measuring their shapes, looking for the faintest distortions caused by invisible mass. It's reading the same book DESI is reading, but paying attention to different details. If DESI measures the rooms, Euclid measures the furniture, the way objects are arranged, the way light falls on them. In March 2025, Euclid released its first results, data from about 26 million galaxies. The survey is about 14% complete. Full cosmology results are expected in 2026, when enough data have accumulated to make precise measurements. We may have new answers within a year, new constraints on W, new evidence for or against evolution. The picture sharpening. What Euclid will tell us is whether the patterns DESI is seeing appear in a completely different method. If they do, the case for evolving dark energy strengthens. If they don't, the question becomes more complicated, and researchers will need to understand why two different methods are giving different answers. Back here by the lamp, we can think of it as reading the same page in two different lights. Natural light from the window, lamplight from the desk. Sometimes the two illuminate different details, Sometimes they confirm what you thought you saw. Either way, you learn something. And there's another telescope coming. The Nancy Grace Roman Space Telescope, a NASA mission scheduled to launch around May 2027. Roman will observe from space, like Euclid, but with higher resolution and a different design. It will have a wider field of view than Hubble, allowing it to survey larger areas of sky in less time. And it will measure supernovae, weak lensing, and baryon acoustic oscillations. All three methods in a single instrument. 3 ways of reading the same pages. 3 independent approaches to the same question. Each one with its own strengths, its own systematic uncertainties, its own way of testing whether W is constant or evolving. By the late 2020s, we'll have DESI on the ground, Euclid in space, and Roman in space, all looking at the same question with different tools, different sensitivities, different systematic uncertainties. If all 3 see the same signal, the evidence becomes compelling. If they diverge, researchers will need to figure out why, and that process itself will teach us something about the methods, the assumptions, the subtleties we hadn't accounted for. Back here in our quiet room, we can rest with that image. 3 telescopes, 3 methods, 3 windows opening onto the same landscape, each revealing details the others might miss. Here's what I want you to notice. This is an extraordinary moment in cosmology. Not because we have the answer, we don't, but because we have the tools to find it. Multiple telescopes, multiple methods, enough precision to measure changes of a few % across billions of years. Think about what that means. For most of human history, the nature of the cosmos was a matter of speculation, philosophy, myth. Beautiful stories, some of them, but stories nonetheless. Then came telescopes. Then came the ability to measure, to test, to ask questions and have the universe answer, not in words, but in data, in patterns of light, in the positions of galaxies, in the way space itself is stretching. The Higgs boson took decades to find. Gravitational waves took a century from Einstein's prediction to their detection. Dark energy's nature might take time too. That's how science works. Not in sudden revelations, but in patient accumulation. Careful measurement, methodical testing. The universe reveals itself on its own schedule. Not when we demand answers, but when we've built the instruments sensitive enough to hear what it's saying. When we've learned to ask the right questions. When we've developed the patience to wait for the evidence to accumulate. And we have patience. The surveys take years. The analysis takes months. The process of checking, testing, reanalyzing, comparing. It's slow, careful work. Not dramatic, not urgent, just steady. If the text is changing, if dark energy is evolving, these instruments will see it. Not immediately, not all at once, but gradually, as the data accumulate, the picture will sharpen. The whisper will either strengthen into a voice or fade into silence. And if the text isn't changing, if lambda is constant, the uncertainties will shrink, and we'll be able to say, with confidence, that the push is exactly what Einstein described. Woven into space-time, unchanging. Either way, we're watching the question resolve. Here in our quiet room, we can feel the privilege of that, of being alive at the moment when the universe is revealing this particular detail. Slowly, patiently, in its own time. The search continues, not with urgency, but with precision, not with anxiety, but with care. The telescopes watch, the data accumulate, the researchers analyze, check, cross-check, publish, and slowly the story clarifies. We began tonight by reopening a question we thought we'd already answered. We learned that dark energy might not be a constant. It might be changing slowly over billions of years in ways that telescopes are just beginning to measure. We learned about W, the parameter that describes how pressure and energy density relate, and how a value of -1 means constant lambda, while any other value means something dynamic. We learned about W0 and WA, the value today and the rate of change. We learned about DESI, the telescope in Arizona that's mapping millions of galaxies, and the hints it found in 2024 and 2025. Whispers in April from 6 million galaxies, then a stronger signal in March from nearly 15 million. Between 2.8 and 4.2 sigma, closer to discovery, but not there yet. And we looked ahead to the next few years, when Euclid and Roman will join the effort, when the picture will sharpen, when we'll know more. Let me step back for a moment and see where we are in the larger story. 5 evenings ago, we noticed the blank pages in the universe's ledger, the missing 95%, the matter and energy that don't shine. We confirmed something is written there. Dark matter, dark energy. 2 distinct presences, 2 different kinds of missing text. We looked at the candidates for what dark matter might be. WIMPs, axions, primordial black holes. Each one a possibility held lightly on the shelf. We discovered that the pages themselves are expanding, that space is stretching, that the universe is not static but unfolding, gently accelerating. And tonight, we explored what that expansion might mean, whether the push is constant or changing, what the telescopes are seeing, what the next few years might reveal. Next time, our last evening together this season, we'll step back and sit with the whole picture. We'll gather the pages we've turned and see how they fit together. We'll look at what we know, what we don't know, and what it means to live in a universe where most of the story is still being written. The book is still open. Next time, we'll close it softly. So where does this leave us tonight? It leaves us in a place of genuine uncertainty. Not confusion, not ignorance, but the kind of uncertainty that comes from standing at the edge of what's known, looking out at what's still being explored. The simplest explanation is still lambda, a cosmological constant woven into space-time, unchanging, fundamental. That explanation fits most of the data, and it requires the fewest assumptions. But there's a growing possibility that the simplest explanation isn't the right one. That dark energy is something more dynamic, more subtle, something that evolves as the universe ages. We don't know yet. The data aren't strong enough to decide, but we're closer than we've ever been to finding out. Back here by the lamp, I want to offer something that might sound strange. There's a comfort in not knowing yet, because not knowing means the question is still alive. It means the story hasn't closed. It means we're living in a moment when the universe is still revealing itself, still unfolding, still offering surprises. If we knew everything, the book would be finished. We'd just be rereading the same pages. But we don't. We're still in the middle chapters, and that means there's still discovery ahead. The universe isn't testing us. It's not withholding answers to frustrate us. It's just being what it is. Vast, ancient, patient, full of details we haven't noticed yet. And we get to be here, in this moment, watching as the details come into focus. Slowly, carefully, gently, so we can set this bookmark here. The equation of state parameter, W0 and WA. Desi's hints from 2024 and 2025. The question of whether dark energy is constant or evolving. The telescopes that are watching. The data that are still arriving. We don't need to hold it all at once. We don't need to solve it tonight. We can leave it on the shelf, resting quietly, while we turn our attention elsewhere. And when more data come in, when the picture sharpens, we'll return. We'll open the book again and see what's been written in the margins. For now, the lamp is low, the room is still. The pages are turning out there in the dark, at the pace the universe keeps. And here together, we can let it be. The lamp is on. That's the first thing to notice, the way it always has been. That particular warmth it makes against the ceiling, the way it settles the room into something smaller and more manageable than the world outside. You may have been here before. In fact, you have been here before, 5 times now, and the room has the feeling of a place that knows you a little. The chair is in the same place. The table is the same table. The window holds its dark rectangle of sky, and the light from the lamp doesn't reach quite as far as the glass. It's a familiar room. There's a quality to that familiarity that's worth sitting in for a moment. When you return to a room many times, you stop noticing it the way you noticed it the first time. You stop seeing it fresh. But sometimes on a particular evening, a last evening, or an evening that feels different from the others, the familiarity becomes something else. Not dullness, more like recognition. Like looking at a face you know very well and seeing it clearly again. This is the 6th evening, and that's how this room feels tonight. There's a weight to saying that, though it isn't a heavy weight. It's more like the feeling you get when you realize a book you've loved is almost finished. Not dread, nothing like that, not urgency, more like a quiet awareness, an attentiveness to the fact that tonight we'll turn the last pages of this particular volume, and that deserves a particular kind of sitting still. The book is on the table. It has been on this table since we first sat down together, and we've added to it, evening by evening, the way you add notes in the margins of something you return to over and over. The spine is familiar now. The cover has the look of something that's been handled with care, picked up and set down, opened and closed, kept close through many evenings. And tonight we're going to sit here, in this room, with all of it beside us, and not rush. There's something to the quality of a last evening that is distinct from all the others. In the middle of a season, each evening carries the sense of continuation. More to come, more to explore, the pleasurable knowledge that there are still pages waiting. A last evening is something else. It becomes its own kind of gift. The room holds everything that came before, and all you have to do is settle into it. and look. So let's do that. Let's not move too quickly. Let's let the lamp do its work, and let the room gather around us, and let the book sit there on the table being exactly what it is. A thing we made together, page by page, evening by evening, in the good company of questions we were not afraid to hold. We're here. The room is quiet. The lamp is on. And this is the 6th evening. Tonight is not a night for new discoveries. I want to say that clearly so we can both relax into it. There's no new chapter we need to open tonight. No new term to understand. No new diagram to place carefully in our minds. Tonight, we are stepping back from the page and looking at the shelf, at the 5 volumes we've arranged across 5 evenings. And we're noticing how they hold each other up. It's a different kind of seeing. When you're in the middle of a book, you're close to the sentences. You're inside the particular word on the particular page. Tonight we get to stand a little farther back and see the whole arrangement. The way the spines line up, the way each volume has its place, the way they make a kind of sense together that none of them made alone. We've been building something, evening by evening. You may not have noticed it as it was happening, because that's how building works. It looks like particular steps, not like a structure, until you step back and see the structure. Tonight we can see the structure. The question we've been sitting with through all 5 evenings is this: what does it mean that most of the universe is made of things we can't directly see? We've turned that question over from many angles. We've held it in many kinds of light. We've looked at what we know and what we suspect and what we simply don't know yet. We've looked at it from the inside, from within the 5%, wondering about the rest, and from what perspective we can manage from here. We're not going to solve that question tonight. I want to be gentle but clear about that. The solving isn't what tonight is for. Tonight is for sitting with the question itself, for noticing what it feels like to have explored it as carefully as we have, and for understanding that living with not knowing is not the same thing as living without knowledge. We know a great deal. We've placed a great deal carefully on the shelf, and most of it points towards something vast, something patient, something that doesn't owe us answers but doesn't withhold them either. Here in our quiet room, with all 5 evenings resting on the shelf beside us, that feels like enough. More than enough, actually. It feels like something worth sitting still with. Let me walk you through what we've placed there. We opened the book and found that most of it was written in ink we couldn't read. That was the first evening's gift, and it was a strange one. We expected, or perhaps we assumed, which is a little different, to find a universe composed of familiar things. The atoms that make up chairs and water and the morning light coming through a window. The cells inside us, the air we move through, the ground beneath us. We have some understanding of those things, hard-won understanding, built across centuries of careful looking. We expected to find more of that. Instead, we found that the familiar things are a thin note written at the front of a very long book. 5 pages in 100 are written in ink we can read. The rest, the vast, patient majority of the book, is something else. Something that doesn't shine, doesn't absorb light the way ordinary matter does, doesn't speak to our instruments in any of the ordinary languages we've learned over all those centuries of careful looking. That first evening, we sat with the strangeness of it. Not the details, but the fact itself. The universe is mostly made of things we can't see. We're embedded in a reality that our senses can barely touch, and our senses were shaped by everything ordinary matter had to offer, not by the invisible, which turns out to be the majority. We are specialized for reading 5% of the book, and the other 95% is written in languages we're only beginning to suspect exist. Back here by the lamp, that fact is still as strange as it was the first night. I haven't gotten used to it. I'm not sure I want to. There's something worth keeping in the freshness of that strangeness. The willingness to let it be strange, even now, even after 5 evenings of looking at it from many angles. The strangeness is real. It belongs to the thing itself. The second evening, we learned that the blank pages aren't truly blank. Something is written there. We can't read it directly, can't point a detector at it and say, there, that word, that sentence, that's what the invisible is made of. But we can feel the weight of it on the page. Galaxies that should have scattered long ago instead stay gathered, held together by something that exerts the pull of gravity without any of the other properties we associate with ordinary matter. A web of structure shapes the large-scale layout of everything we can see, running through the universe like the framework of a house visible only through its effects on what rests against it. We couldn't read the words, but we could feel the weight of them. That's how the second evening felt. Not a lapse in seeing, but a kind of oblique seeing, like noticing a heavy object because of the impression it leaves in a cushion, not because you can see the object itself. The impression is real, the weight is real, the something there is real, and there's a precision to how we know it. The weight isn't vague or approximate, it has a ratio. The invisible scaffolding is several times more massive than all the ordinary matter in the universe. All the stars, all the gas, all the atoms of every kind that have ever formed in the history of everything. The invisible is not just slightly more, it is dominantly more. The ordinary is the minority in a universe shaped by something we can't see. Back here by the lamp, that weight is still present. We don't need to see it to know it. That knowing, that oblique and confident knowing, is itself a kind of understanding. It's the kind of understanding the universe rewards when we pay close enough attention to what it's doing, rather than what we expect it to do. The third evening, we looked at what the invisible writing might say. We brought out what the researchers have proposed. Particles that move slowly and quietly through the universe, interacting only through gravity and perhaps one other force, leaving no footprints in ordinary detectors and no impressions on light as it passes through. Fields that pervade everything without announcing themselves. Remnants of the universe's earliest moments. Fossils of conditions that lasted only a fraction of a second near the very beginning, when the rules of matter were being established for the first time. Each one a possibility resting on the shelf, none confirmed. Each one waiting patiently for the instrument or the observation that will either bring it into the light or return it to the margin. We looked at each of them carefully that evening, tried to understand what it would mean if any of them turned out to be right, and discovered that each answer would bring its own new set of questions, which is, of course, how this works. That evening taught us something more than the candidates themselves. It taught us patience. The universe doesn't rush its answers. We can propose and refine and test and wait, and the universe simply continues being what it is, whether or not we've guessed correctly. The candidates sit on the shelf regardless. The universe contains what it contains. Patience. That's what that evening was about. The patience to hold a possibility without collapsing it into either proof or dismissal. The fourth evening we turned to a different kind of invisible entirely. It wasn't hidden inside things the way dark matter seems to be, not embedded in the invisible scaffolding between the galaxies, not a particle or field drifting through ordinary space. It was something more fundamental. It was a property of space itself, something pressing outward from within the fabric of the universe, as though space itself had a preference for expanding rather than remaining still. We discovered that the book isn't static. It's growing, gently, patiently, stretching in all directions at once. Not because of anything inside it, but because the space between the pages is widening. The pages themselves are being carried apart. A galaxy on one page and a galaxy on another are not moving through space so much as the space between them is quietly, steadily increasing. Dark energy, the cosmological constant. The simplest name we have for the thing we understand least. We turned it over carefully that evening, placed it on the shelf with care, and admitted that even the medium, even the paper, even the binding, even the space the book exists inside, is part of the mystery. We're not only reading a text we can't fully see, we're reading a text in an ink whose material we don't understand, in a volume whose structure is itself unknown, whose edges we can't locate. That's a particular kind of wonder. Not threatening, nothing like that. Something more like awe at the scale of what we're inside. Last time, we asked whether the push is the same push it's always been. We met a new instrument, a careful and systematic mapmaker, laying down the positions of millions of galaxies across enormous distances, building a three-dimensional portrait of the universe's structure that has never existed before. And that mapmaker offered us something interesting. A hint, not an answer. A hint that the gentle push might not be as constant as the simplest explanation requires. That it might be changing, evolving slowly across cosmic time. Something more dynamic than a fixed property of space that never varies. The researchers are cautious about that hint. They discuss it carefully. They look at what the data can support and what it can't. They compare it against other measurements and other methods, and they find that the question is genuinely open in a way that careful science keeps open. Not refusing to answer, but not pretending the evidence is more definitive than it is. Hints, not answers, and not the last hints either. The instrument is still gathering. The data are still being examined by careful hands. There will be more. We left the question open last time, because the question is still open. The telescopes are watching. The data are accumulating. And we placed a bookmark in a page that is still turning. A page whose next line hasn't been written yet, or hasn't been read yet, which amounts to the same thing for us. And here we are, the sixth evening, all 5 chapters on the shelf beside us. The room holds them all, and the lamp gives the same warm light it always has. So what don't we know? Let's be honest about the gaps. We don't know what dark matter is. This is worth saying plainly, without softening it into comfortable vagueness. We've confirmed that something is there, We've confirmed it's not made of the ordinary atoms we are made of, not light we've missed, not compact objects hiding in plain sight. We've eliminated possibilities one by one, narrowing the territory where the answer might live. And the most sensitive detectors ever built, chambers of extraordinary quiet, buried deep underground, shielded from every background they could be shielded from, have been listening carefully for years. They haven't heard anything. This isn't a shortcoming. That framing doesn't belong here. But it is an honest gap, and the gaps deserve honest acknowledgement. The something there is real. The what it is remains unknown. There's a detail worth carrying gently from this search. The detectors have become so sensitive that they're now picking up neutrinos, tiny, nearly massless particles streaming continuously from our own sun in extraordinary quantities. That's actually remarkable. The instruments are so quiet, so attuned to the faintest possible signals, that the whisper of the sun itself is now audible from deep underground. That background whisper makes the search harder, in the way that a familiar sound in the room makes it harder to hear a sound from outside the room. The instruments have to learn to listen past the familiar in order to catch something new. So far, that something new hasn't spoken. The search continues. The chambers remain open and quiet and waiting. We don't know what dark energy is. The simplest explanation, a fixed energy of space itself, uniform and unchanging since long before any galaxy formed, fits most of the data well. But the hints from recent surveys suggest there may be more structure to the story, that the push might have varied over time, that the simplest explanation might be a very good approximation of something slightly more complicated. And there is a disagreement, a careful, ongoing, deeply interesting disagreement between different methods of measuring how quickly the universe is currently expanding. Different approaches, using different instruments and different reference objects, arrive at numbers that don't quite agree with each other. Either one of the methods has a systematic error that hasn't been found yet, or the universe is doing something that our current picture doesn't fully include. Here by the lamp, we can hold those gaps without anxiety. They're not cracks in the floor, they're doorways. Each gap is a place where the next chapter is waiting, not hidden maliciously, but simply not yet reached. The history of cosmology is a history of revised expectations. A century ago, the settled picture was a static universe, vast, eternal, changeless. The idea of a universe with a history, a universe that began differently than it is now, and will end differently than it currently appears, wasn't part of the standard account. The stars were old and stable. The arrangement of the sky felt permanent. Then careful measurements came in, and redshifts accumulating across many distant objects, and the static universe gave way to an expanding one. The revision was profound. It changed what questions were even askable. 70 years later, the settled picture was an expanding universe that was slowing down, stretched thin by the energy of ordinary matter, gradually decelerating under the pull of gravity toward whatever comes next. Then the observations came in, mapping distant events across time, and finding that the universe's expansion wasn't slowing at all. It was speeding up. The decelerating universe gave way to the accelerating universe, and the revision was, again, profound. Each generation builds on the previous one. Each generation's certainties become the next generation's starting points. And sometimes, the next generation's surprises. Each generation discovers that what they took as the whole picture was a chapter, a beautifully coherent, carefully assembled chapter, inside a book that turned out to be longer and stranger and more detailed than they expected. The pattern is consistent enough that it deserves to be taken seriously. Each generation opens the book expecting to find the last chapter, and instead finds a new volume. If history is any guide, and it is a thoughtful guide if not a perfect one, the next surprise is already in the data somewhere. It may be the disagreement in expansion measurements. It may be something the next generation of instruments will reveal. It may be something no one has thought to look for yet. That's not unsettling, or at least it doesn't have to be. The universe has consistently turned out to be more interesting than our current picture of it. That pattern, taken seriously, is its own kind of reassurance. Not knowing isn't a burden. It's a sign that the story is still being written. Richard Feynman, one of the most careful and playful thinkers physics has produced, said something I've been carrying through this entire season, something that belongs in this room tonight. He said, "I can live with doubt and uncertainty and not knowing. I think it's much more interesting to live not knowing than to have answers which might be wrong." I want to sit with that for a moment, because it's easy to pass over it too quickly. He's not celebrating ignorance. He's not suggesting that questions don't matter or that the search isn't worth conducting. He's saying something more precise and more interesting, that a false answer is worse than an open question, that the comfort of a finished book is the comfort of something closed, and closed things don't grow, that the willingness to remain genuinely uncertain, to hold a question as a question, rather than collapsing it prematurely into an answer, is actually a kind of intellectual courage and a kind of pleasure. Imagine if we knew everything. The book would be done, every page filled in, every margin annotated, every footnote explained, every question resolved. There would be nothing left to discover, no new instrument to design, no new question to formulate, no morning where a data point arrives and changes the shape of what we thought we understood. No more evenings like this one, sitting together with a chapter we haven't fully read, wondering what it might contain. Which would you rather hold? A book with every page filled and nowhere left to go, or one with most of its chapters still being written? The universe is patient. It doesn't mind that we haven't solved it. It's been keeping its own counsel for nearly 14 billion years, and it will continue to do so. The questions remain open, the instruments keep listening, and we don't need the answers tonight. Here in our quiet room, we can rest with that. The questions are real, the search is real, and the not knowing is part of the gift. But the work continues. Let's look at what's still being written. Even as we sit here, the work is ongoing. There's something steadying about that. Not urgent, nothing like a countdown or a deadline, but a quiet satisfaction in knowing that the instruments don't pause. That somewhere, right now, at this moment, telescopes are open to the night sky, gathering light from distances that take billions of years to cross. Detectors are underground in the deep quiet, listening for something they haven't heard yet. Computers are sorting through the shapes of galaxies mapped across years of patient observation, looking for patterns that might not be visible to any single mind, but emerge only when many careful minds work together on the same body of evidence. The instrument we learned about in our last evening, the careful map maker, the one building a three-dimensional portrait of the universe's large-scale structure, is completing its 5-year survey in the coming months. The most detailed such portrait ever assembled will be finished and in the hands of the researchers who will spend years drawing meaning from it. That portrait may tell us whether the gentle push has changed over cosmic time, and if so, by how much and in what direction. It may strengthen the hints of the most recent analysis, or it may revise them in ways that neither confirm nor dismiss the question, but rather refine it. We don't know which. That's exactly as it should be. A telescope mapping the sky from space, patient and orbiting, free from the blurring effects of our atmosphere, will release its first major cosmology results later this year. Fresh measurements, fresh mapping, fresh eyes looking at how matter is distributed across the universe and how the expansion has unfolded across time. What those eyes see may settle some of the ongoing questions, or it may open new ones. Either outcome moves the work forward, and the Roman Space Telescope, launching next year, will open a window onto the early universe vastly wider than anything we've had before. A view 100 times larger, reaching back across time to conditions we've only been able to glimpse at the edges of what current instruments can reach. What lives in that wider view, we don't yet know. Underground, the next generation of dark matter detectors is being designed and planned. Larger chambers, deeper quiet, finer instruments, reaching further into the silence, listening for something quieter than anything we've been able to detect yet. Not with urgency, but with the patience of work that knows it might take time and is prepared to take the time it needs. New reading glasses, better light, more careful hands turning the pages. The work continues whether or not we're watching. That's one of the things I find most settling about science as a human activity, that it is passed from hand to hand, a community endeavor that doesn't depend on any single person's attention or persistence. The work was happening before we sat down together. It will continue after we close the book tonight. Within the next few years, we may have answers we don't have now. We may learn whether dark energy is truly constant, a fixed property of space that has always been exactly as it is, or whether it has varied across cosmic time. If it has varied, that variation will tell us something profound about the nature of space itself, something that the simplest explanation couldn't predict and couldn't explain. The distinction matters. It changes what kind of universe we're in. We may detect the particle, or field, or structure that dark matter is made of. If we do, it will be one of the most consequential discoveries in a long time of consequential discoveries. It will change the questions we can ask about the very early universe, and about how structure formed, and about what the future of the cosmos might look like. Or we may find that whatever dark matter is, it interacts even more quietly than our current instruments can reach, and we'll need to imagine entirely new approaches, new questions, new geometries of search, new ways of listening. We may resolve the disagreement between different measures of expansion, or we may find that resolving it requires something the current picture doesn't include, a new chapter that no one has drafted yet, a revision that changes what came before without erasing it. The questions are getting sharper, the instruments are getting more sensitive, and the universe is still out there, being what it is, whether or not we're paying attention. We might be surprised. We've been surprised before, not once or twice, but repeatedly, as a pattern, as a feature of how this kind of searching tends to go. The universe has consistently turned out to be more detailed and more strange than the most careful minds of each era expected. There's no particular reason to think that pattern has ended. The book still has unread chapters, and we're building better reading lamps. Here, by the lamp, we can trust that the work will continue. People we'll never meet are already planning the observations and experiments that might change the shape of the next volume. That's its own kind of gift, the knowledge that the story belongs to more than any one of us, that it's larger than any single season of reading. But tonight isn't about the future. It's about what it means to be here, now, in this particular moment. Here by the lamp, made of the 5%, reading about the 95. That's actually what's happening right now, in this room. The lamp itself is made of atoms, the filament or the circuitry, the glass, the wire, the switch. Atoms organized into something that produces light. The chair is made of atoms. The table is made of atoms. The book on the table, the paper, the ink, the binding, all of it, atoms. And we ourselves, sitting here in the quiet of this late hour, thinking and wondering and listening, are made of atoms too. Atoms organized into something that can look outward at the universe and wonder about the rest. Carl Sagan, who thought as carefully and as warmly as almost anyone about what it means to be a small and particular thing inside a vast and mostly unknown cosmos, said something that belongs in this room tonight. He said, "We are a way for the cosmos to know itself." That line has the quality of a room anchor if you sit with it long enough. The cosmos is mostly dark matter, mostly dark energy, mostly things we can't see, can't directly touch, can't bring into the ordinary light of experience. And yet, in the 5%, something assembled itself. Through a long and patient process of stars forming and scattering their contents, and new stars forming from the scattered contents, into beings capable of asking questions about the 95, capable of building instruments and analyzing data, and wondering, in a quiet room late at night, what the invisible is made of. We sit in this room, made of atoms, surrounded by a house made of atoms, in a universe that is mostly made of something else entirely. And here we are, asking questions about it. There's something remarkable in that. Not humbling exactly, or not only humbling, more like wondrous, like the discovery that the small thing you are is not separate from the vastness you're trying to understand. You're part of the same story. You are the chapter the story has written to read itself. Back here by the lamp, that feels worth holding for a moment. Just letting it sit in the warm light alongside everything else we've placed on the shelf tonight. Every civilization that looked at the sky knew it was looking at something vast and mostly hidden. Ancient astronomers mapped the patterns of stars without knowing the stars were suns. They tracked their movements across seasons, built instruments of remarkable precision to follow the wandering lights through the fixed ones, assembled calendar systems and navigational charts and mythologies that tried to make sense of what they saw. Their observations were careful, their records were often extraordinary, and they understood almost nothing about what the lights actually were, what burned inside them, how far away they stood, what relation they bore to the warmth of our own daylight sky. Hubble, in the 1920s, measured the redshift of distant objects without knowing that the accelerating expansion of the universe was waiting to be found. He saw something real and reported it carefully, and contributed to a revolution in understanding. But the implications of what he saw took decades to unfold, and some of those implications hadn't even been imagined when he was working. Perlmutter and Schmidt and Rees, in the late 1990s, set out to measure the rate at which the expansion was slowing, a question they thought they understood well enough to go study carefully. What they found was that the expansion wasn't slowing at all, it was speeding up. The question they went in to answer was not the question they came out with. Each generation sees a little more. Each generation's everything turns out to be a fraction of what comes next. We're in that position now precisely. We see 5%. We've confirmed the other 95% exists and acts on the things we can see. We know the blank pages hold something real. We just haven't learned to read them yet. Back here by the lamp, we're part of that chain. We're the generation that confirmed what the blank pages contain. Not the words, but the weight of the words. The generation that first caught hints that the push might be evolving. What the next generation makes of those hints, and what they discover when they look even more carefully at what we've found, we can only begin to imagine. You don't need to understand dark matter to live well. That seems worth saying plainly, in this room, on this last evening of the season. You don't need to solve the vacuum energy puzzle to sleep tonight, or to find meaning in tomorrow, or to feel that your particular life inside the 5% is a worthwhile one. The questions we've been exploring across 5 evenings are real and important and fascinating, and they will be investigated by careful people for a long time to come. But none of them require your personal resolution. They're not a burden you've been handed. What they are, and this is what I want to offer in these last pages before we close the book, is an invitation. An invitation to notice that the reality we're embedded in is vastly larger and more interesting than any account of it we've yet managed to write. An invitation to find that enlarging rather than diminishing. An invitation to let the not knowing be a kind of spaciousness rather than a kind of gap. There's something deeply human about wanting to know, about looking at the night sky and asking questions. Not because the answers are immediately useful, not because knowing what dark matter is will change the quality of tomorrow morning, but because the wanting to know is part of what we are. We've been doing it for as long as we've been doing anything that looks like culture and civilization, and probably longer than that, when the impulse was less articulate but no less real. The questions aren't burdens, they're gifts. Each one is a doorway in this house that hasn't been opened yet. Not locked, not forbidden, just not yet reached. The house has many rooms, and many hallways, and many doors, and some of them we've walked through this season, and found other rooms inside with their own doors. And some of the doorways are still at the end of the hallway, simply waiting. The universe is not secretive. It doesn't withhold its answers out of spite or indifference. It simply has more rooms than we've had time to find. It leaves clues. The clues are real and detectable and meaningful, and we've found some of them together across 5 evenings. We just haven't found all of them yet, and there's no particular reason to expect we would have. Here in our quiet room, the doorways wait. They're not going anywhere, and neither is the universe, which is patient in a way that makes our occasional urgency look like a very particular and very human kind of charm. Let's close the book. The book is on the table. It was on the table the first night when we opened it and found the blank pages and sat with the strangeness of the fact that most of the universe is made of things we can't see. It was on the table the second evening when we learned that the blank pages have weight. It's been on the table every evening since, through the candidates and the gentle push and the hints of change and all the careful conversations in between. It has stayed in its place, on this table, in this light, while we've done the slow work of reading it as carefully as we could. We opened this book 6 evenings ago. We've turned its pages slowly, the way you turn pages when you want the reading to last. We've read what we could and marked what we couldn't yet understand, and placed small, careful notes in the margins where we wanted to remember something. The book is different now than it was when we first sat down together. Not its contents, we didn't add to those, but our relationship to it. We know it better now. We've spent time with it. Now it's time to close it. Not because the story is finished. It isn't, not even close. The story has been unfolding for nearly 14 billion years and will continue unfolding for far longer than any of us can hold in mind. The work of reading it has been ongoing for a few centuries in its current careful form, and there are long chapters still ahead. The story is very much ongoing, but we've read enough for one season. And there's a rightness to closing a book at the right moment. Not when it's finished, but when you've taken in as much as you can hold, and you want to rest with what you've found before you reach for more. Let me trace the thread one last time from the beginning. We noticed the blank pages, the fact that most of the universe is written in an ink our instruments can't yet read, that the familiar 5% of ordinary matter is a small note at the front of a very long book. We confirmed that something is written in the rest of the pages, something real and weighty and structurally important, even if we can't see it directly. We looked at the candidates for what that writing might say, the possibilities resting on the shelf, each one waiting for the observation that will confirm or revise it. We discovered that the pages themselves are expanding, that the book is growing gently in all directions, not because of anything written inside it, but because of something woven through the space between the words. We explored what that expansion might be made of, whether it's a fixed and unchanging property of space or something more dynamic. And we found that the question is genuinely open, that hints are accumulating, and that the clearest answers are still being gathered by the instruments that are watching even now. And tonight, we sat with the whole picture, the knowing and the not knowing, placed side by side on the table. The things we've confirmed and the things we haven't found yet. The instruments that are working and the questions that are getting sharper. The history of revision that tells us the next surprise is waiting somewhere in the data. And the particular pleasure of living at a moment when that surprise hasn't arrived yet. This is the book of the missing 95%. Most of it is still unread, but we know it's there. We know the blank pages hold something real, and that knowledge, the confident knowledge that the invisible is real, that the questions are meaningful, that the search is worth conducting and is being conducted with care, is itself a kind of beginning. Not an end, a beginning. We leave the season at a threshold, with 5 volumes on the shelf, and the hallway continuing. The lamp is still burning. The room is still here, as it has been across 6 evenings. The chair, the table, the window with its quiet dark beyond the glass. The shelves hold everything we've discussed, the dark matter and the dark energy, the candidates and the hints and the open questions, the history of revised certainties and the pattern of recurring surprise. All of it is still there, and it will be there when you want to return to any part of it. You don't need to hold any of it tonight. That's not what tonight is for. It will all be here when you come back to it. The instruments will keep watching, the map makers and the space telescopes, and the underground chambers listening in the quiet. The researchers will keep analyzing, the data will keep accumulating. The work doesn't require your vigilance to continue. It is happening, steadily and patiently, whether we're attending to it or not. The universe is patient. It has been unfolding for nearly 14 billion years, and it has been entirely unconcerned with whether any particular observer was paying attention on any particular evening. It will continue unfolding. The rooms we haven't found yet will still be there. The doorways in the hallway will still be waiting. The blank pages will still hold what they hold. It won't mind if you rest. The book is on the table. The lamp is low. And outside, in the vast quiet between the galaxies, the pages are still turning, gently, patiently, whether anyone is reading or not. Rest well.